Okay, we're back here at the top of the hour. I think that to stay on schedule, we'll get going. I'm very happy to introduce to you Professor Michael Jordan, who's giving the summit keynote address today. So if I don't think Dr. Jordan needs any introduction, but I will anyway. He's the Pihong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at UC Berkeley. He received his master's in mathematics from Arizona State University and his PhD in cognitive science from UC San Diego. Prior to his appointment at Berkeley, he was also a professor at MIT. His research interests bridge the computational, statistical, cognitive, biological, and social sciences. He's a prolific author in these areas. If you look at his Google Scholar, his publications have received nearly 250,000 citations. These works have received many awards and recognitions. I don't have time to list all of them. We want to hear what he has to say, but I will list a few of them. Professor Jordan is a member of the National Academy of Sciences, a member of the National Academy of Engineering, and a member of the American Academy of Arts and Sciences, and a foreign member of the Royal Society. He is a fellow of the American Association for Advancement of Science. He was a plenary lecturer at the International Congress of Mathematics in 2018. He received the Ulf Grenander Prize for the American Mathematical Society in 2021, the IEEE John Van Neumann Medal in 2020, the IJCAI Research Excellence Award in 2016, and also in 2016, he was named the most influential computer scientist in the world in an article in Science. So it is our great pleasure to have Dr. Jordan with us today. As you can see on the screen, he's going to talk to us about machine learning as statistical learning, computational, inferential, and economic perspectives. So thank you on behalf of the organizing committee, Dr. Jordan, for taking the time to be with us today, not just for this keynote, but also for the panel discussion that's coming up in an hour or so. So thank you.
Thank you very much. Thanks for the introduction, and really my pleasure to join you. If there are any logistical glitches with slides or audio, please let me know. Okay. Yes, anyway, glad to be here. Glad to have a discussion with you this morning. I do think you are onto something as a community with this notion of statistical engineering. And really, I guess one of the things I want to do is talk about the scope of what that might be. And I'm going to be really taking a perspective of someone who works a lot in industry. I do think that our field, whatever you want to call it, is an outward looking field. And really the question is, what's on the other side of that outward look? Who do we engage with and for what purpose? So what are the phenomena of the era? And so on. And so I have the phrase machine learning here, just because in the outside world, if you go to companies, they often use the phrase machine learning to describe what we might call statistical engineering. They also nowadays even more just use the phrase AI, sort of badly. So the question is not going to be to define those terms or delimit them per se or relate them. They really, I think, reflect the same underlying phenomenon. And I want to talk more about the phenomenon and then what might be the scope of this emerging phenomenon and how do we respond to it and what do we want to tackle as the full scope of it. So this is a slide I've been using for a few years now. In fact, before I was aware of some of the work that you folks have done. But I was trying to understand what this thing called machine learning was. Again, it's being used a lot in industry, and it kind of reflected at some point the need to have people who had both statistical education and computer science education. Then the word data science became used for a very similar set of issues. Academics then have scrambled around to kind of define each of these things and have curricula and so on. But I think that's somewhat missing the point. I think it really is driven by the outside world. And I think that the best metaphor eventually came to mind was that it wasn't an academic creation at all. It wasn't a new field of inference. It really was statistics kind of conceptually, but it had a different flavor. And I think it was akin to the difference between chemical engineering and chemistry. So, historically, pseudo-historically at least, in the 40s or 50s, chemical engineering emerged. It didn't exist before that as a discipline, but you already had explanatory principles. You had chemistry and fluid mechanics and quantum mechanics and so on. So you understood what happens when you put chemicals together. But what you didn't have is the notion of scale. I mean, you didn't have the notion of the ability to design and build a factory that would make products at scale for large numbers of people that would be economically viable and so on. So a field emerged as people were building factories. They also had a field emerged called chemical engineering. And it had its own mathematics to it. There, new thermodynamic principles at scale, new fluid flow principles, and so on, needed to be developed. And if you are a chemical engineering student, you'll study that mathematics. So it's not just engineering; it has its own mathematical ideas in it. Electrical engineering, I know a little less about the history, but clearly there was electromagnetism before that. There was Maxwell's equations and some understanding of electrical flows. But the idea of putting circuits together and having power brought to homes and so on required, again, brand new ideas. And if you study electrical engineering, you engage in that kind of mathematics of electrical engineering. So I think that we are seeing an emergence of something new that has an engineering flavor. It's based on flows, it's based on networks. Computer networks underlie all of it, but it's not about the computer networks per se. It's about the value and the data that flow over those networks and how they link people. So this, I think, is the first engineering field that really where people and people's decisions and transactions and behavior is integrally part of the engineering discipline. It's not an afterthought or a secondary aspect of it. So, many companies have been, of course, building systems that do this. Companies that do e-commerce, companies that do finance, transportation, you name it, are building large, in fact, even planetary scale systems that are fundamentally based on inference and prediction and decision making under uncertainty and so on. So those artifacts, whatever you want to call them, they certainly have a statistical and an engineering flavor. You notice the word science doesn't appear here at all. And I think a slide we may talk about later that I also used is that I questioned why science becomes the priority for statistics, that scientific discovery is certainly the history of statistics. It's, we think of ourselves as embedding ourselves with teams to make scientific discoveries. But engineering is as important to the human species as science is. They obviously go together, but building artifacts in the real world that never existed before, I think civil engineering also, has changed our life more than just about anything you could imagine. So contributing to a new engineering discipline, its birth and its shaping seems really, really important to me, in addition to any role we play as helping scientists make discoveries. Okay, so today's talk, I want to emphasize the three foundational disciplines. It's often been emphasized that there's statistics and computer science kind of being brought together, but I'm going to emphasize in this talk economics. And this partly came again from being in industry and watching problem solving around the table, where a system was being designed, inferences were made, data was being collected, and then it was being deployed in the real world, and suddenly interactions and strategic agents came into the focus and into play. Game theoretic concepts came out, and it was clear to me that that was just the tip of an iceberg, that there was a whole economic model needed to be understood and developed in concert with statistics and computer science. And if you think about the connections between these fields, of course, they already exist at some level, but they're really dyadic. So statistics merging, blending with economics, that's econometrics. But econometrics has had a limited goal. It's mostly about measuring economic phenomena. It's time series analysis, a bit of causal inference. It's less about designing economical systems. It's less about what's called mechanism design in economics, and it's also less about large-scale distributed computing and networks and so on. So it doesn't have much of the computer science algorithmic flavor that we might expect from a broader discipline. Similarly, statistics coming together with computer science, that's really machine learning. And I'm going to use the phrase machine learning broadly here. It's not just a class of techniques for making predictions. Someone who calls themselves a machine learning researcher generally will also talk about decision making around uncertainty and talk about building large-scale platforms and so on and so forth. Right, but what they kind of are missing, I think, is the economics perspective. They don't have the perspective of strategic agents who are possessing data, acting on data, having self-interested, having vested interest in the outcome of a data analysis. And I'd argue, in fact, statistics doesn't have very much of that perspective either. Now, economics with computer science, that has a name as well. That's called algorithmic game theory. And there are textbooks on this. That field exists. It's maybe less known to some of you, but it exists, and it has real contributions. A core part of that are things like algorithms for matching markets. So kind of the microeconomics meets computer science. Again, it's a dyadic connection. What it's missing is statistics. It tends to assume that things are known a priori and just worry about the algorithms and the stability properties. It's missing statistics. All right, so I hope the message was kind of going to be clear that emerging problems in real life blend all three of these perspectives. You have self-interested agents, you have strategic data gathering, you have to put that in an algorithm and computer platform, and you have to use statistical inferential perspectives to inform all of these things. So whatever you want to call all of this mix, there are real world problems that very much have this flavor. And so I want to emphasize in this talk kind of the economic side of it, because I think it's probably less emphasized. And at least to me, it's very much in scope. Okay, so let's use this phrase machine learning for a while. Again, I'm not trying to define it as a subset of anything or related to anything. If you want to place statistical engineering instead of machine learning here, that's perfectly fine. Let's just recognize that it has had a big impact on our world, and it's not easy just to define that impact. But pattern recognition is another terminology that's used to describe much of what the impact has revolved around. Platforms like TensorFlow and PyTorch have been essential. So the computer science contribution is in part to build large-scale platforms that run on commodity hardware and don't run just on one laptop, but run just as easily on 10,000 laptops and can be used for very, very large-scale data analysis. And so sometimes you don't hear people in industry even knowing that this is statistical prediction or inference. They just think of it as AI or machine learning because of the platform that calls it that, and they simply use it in that way. So they may be doing a linear regression or a logistic regression, thinking of that as AI and pattern recognition. So that's certainly one side of machine learning, and it's one side of statistics. But more broadly speaking, statistics and machine learning have a decision-making side. In statistics, we often start with decision theory, but then we move on quickly to inference and regression and so on. And I want to restore decision-making to its rightful place here. And also the machine learning people tend to not think about it less as well. They have a separate branch of ideas that don't make that much contact with pattern recognition. So we'll talk a little bit about individual high-stakes decisions and then get all the way to market mechanisms where lots of decisions are interacting and start to talk about what are the intellectual issues at play there. Okay, so just a slide to remind you of kind of what we might view as pattern recognition. This is a thing that's had a huge impact, at least in the real world. It's had an impact. It's certainly in our media. It's talked about a lot, and there are use cases in industry that are impressive. Whether it's going to have a huge impact on productivity going forward is not entirely clear, but probably. So deep learning has become the dominant paradigm here. It really is a form of regression. It requires input-output or covariate response pairs. It's fitting a surface to high-dimensional data, and it uses a gradient descent method to adjust the parameters of this. So it's very statistical in flavor, but you tend to be focused more on the output, the prediction, and less on the inferential properties of it. But that's just that's some people's focus. It's become so widely deployed that just really there's a subgroup focused on any aspect of it, including error bars and inferential things and model selection and you name it. So many real world examples: credit risk assignment, computer vision, robotics. All these problems in the real world are these architectures are being used. Okay, so I'll not say anything more about that. Let's just be aware that's kind of the context. All right, now let's turn to decisions. So you might think that a decision is kind of a thresholding of a pattern recognition device, and I'm going to argue that's not really a useful perspective in consequential real life decisions. So to be very concrete, let's consider you go to your doctor's office in a few years, and the doctor has available to them a large deep learning system that's been trained on all the world's medical data. So the hospitals have all aggregated their data, and just everything that's relevant to medicine has been put in there, and it's been used to train this neural net that makes predictions based on someone's body state, a prediction of their health status, or what the probability they're going to have various diseases, and recommend treatment options. So suppose you arrive and they measure 100,000 things about your body, including maybe they sequence your entire genome, and they put that into that neural network. and let's suppose that one of the outputs of that neural network is a prediction about heart disease, and based on all the historical data, that goes beyond what any human has ever looked at, if a number is over 0.7, that suggests you're about ready to have a heart attack and you should have an operation ASAP. And suppose your number is 0.701. Now you're over the threshold. You should just think of that as a decision by the smartest system ever built and just kind of adopt it. The answer is probably no. You're going to, first of all, you're going to make some inquiries, like what is the error bar on that? How sure are you of that at 0.701? And I don't mean just a little Gaussian error bar or a permutation test error, or a sampling error. It really has to do with where the data came from, how old are the data? Are they recently collected, maybe 10 years old? That would increase my uncertainty. Was it collected on a machine like the one used for me? Was it collected on people like me? And so on and so forth. And all those things should contribute to your notion of uncertainty. And in the context of the doctor's office, sitting and having a dialogue with a doctor, you may never write down these uncertainties, but in your mind, they're arising. And a good engineering system should kind of have them there. So somehow, like a database system that has notions of provenance, of where data came from, and metadata, as you started to have a dialogue about your particular decision, the error bar should be adjusted accordingly. Moreover, you're going to ask questions of your doctor about alternatives, alternative explanations. You're going to remember things you hadn't remembered before. For example, I had asthma when I was a child, or my parents had a heart condition. I forgot all about that, and now I remember it. And you're going to realize that that pattern recognition device did not have all the world's medical data in it, in the sense of it's in the moment of a particular decision about your heart disease. There's all kinds of new things that become relevant that weren't relevant before. And so a good doctor will then take that in as data effectively and readjust and make new predictions, effectively doing counterfactual analysis in the moment. And you will be reasoning in the moment about this in a dialogue with your doctor. And so a good statistical system should support all of this. It should be doing all of this adjustment and rerunning data analysis in the light of new information that's being discussed as part of that dialogue. So that's what real decision making is like, and reducing this to decision theory and a threshold between two Gaussians and all really damages the serious dialogue nature of a real world decision that's consequential for anyone in their real life. And it doesn't have to be medical, it could be anything. So today I'm going through many decisions, and they're at different scales. Some of them are on the scale of minutes or hours. Some of them are decisions I'm doing in my life at this period of time. All right, so there's consequences, there's counterfactuals, there's provenance, and so on. And any system that purports to aid in decisions has got to participate in this. So it's, moreover, it's not just my own decisions, it's me linked with other people across networks. Even the health system, if a drug is tried on someone somewhere and it works, the system should pretty quickly make that data available to other doctors to be used for other patients. So we're linked in some ad hoc sense, and the pandemic has kind of revealed this. We're linked by the decisions made for other people on us. And this happens over time, it happens asynchronously. And in the medical system, it's very ad hoc, all of these linkages, but in something like transportation or finance or commerce, it's less ad hoc. There really are real existing networks that make these kind of connections. So I'm starting to move towards economics as I'm in this discussion. If you start to make decisions in the real world, there will be interactions among the decisions. There'll be scarcity and competition. And so a good decision is no longer definable even in isolation. It depends on what other people are doing and depends on trade-offs. So now we're really in the world of economics. So let's again be very concrete to get there. Let's talk about recommendation systems. So this is definitely an engineering artifact. A recommendation system is a commodity piece of software that you can download. It takes in data in the form of a big matrix. For example, customers and the items they purchased, or viewers and the films they viewed, and so on. And you can analyze this data with some kind of a matrix-oriented analysis tool and make predictions effectively and treat them as recommendations for people. And you've all used these, for example, recommending books on Amazon or movies on Netflix, but they're used now throughout e-commerce. In fact, it's kind of a multi-billion-dollar contribution to productivity. So these are prediction devices. Are they really also, can you think of them as decision making? They do make recommendations after all. And I would argue that they're very ineffectual if you think about them in the real world. So imagine that you've developed an analysis, a recommendation system, and it's a piece of software that people can use in various business models. And suppose that everyone in some city is using your app. And so your app might maybe make movie recommendations to people like Netflix does. If everyone in some geographical region is using your app, then you could easily recommend the same movie to 100,000 people. And that's not a problem because there's no scarcity in the world of bits. You simply copy the bits to everybody. If you recommend the same book to everyone, I'm sure this happens to Amazon on many days. You recommend the same book to 100,000 people. And many of them might want to buy that book, and there's something called print on demand that allows you just simply to print as many copies as you need. So there's no scarcity there either. But is there really scarcity anymore? And of course there is. And so just think about an app now that makes restaurant recommendations. Right now, there's not very good apps for this. If you are in Shanghai and you're out on the street and you don't speak Mandarin very well, and you bring up some browser and say restaurants in Shanghai, you're going to get a lot of junk, a lot of advertisements, or a lot of irrelevant material. So really what needs to be happening there is you need a recommendation system that is a little more of a in the moment, recognizes where you are, your taste, and so on. All right, but let's suppose that someone's designed that and people are starting to use that in some city. It again could recommend the same restaurant to maybe 10,000 people. And now you've created congestion. People will all go there and they'll be unhappy they can't be served. Same thing if you're recommending streets to drivers. What's the fastest route to the airport? Well, if you recommend that route to a few people, no problem. If everyone's using your app, you'll send too much traffic down that street and create congestion. Recommending stock purchase to people, you can destabilize the market this way and so on. So how do you fix this? And here I really think that Silicon Valley doesn't have good ideas about this. They think about this as a load balancing problem. The system made the best predictions it could, and now you have to balance that in some way, be fair. And even worse, Silicon Valley thinks that from your browsing history and doing statistical data analysis on your browsing history, they'll know enough about you that they can predict what you really would like, and they will send you to the restaurant you really prefer or down the street you prefer. And I hope that you agree this is really silly and it's moreover invasive. Really what we want to be involved in these kind of decisions is part of a market. And a market just means a connection between producers and consumers such that there are valuations that each person on one side values things on the other side, and the valuations may change and fluctuate in the moment depending on all kinds of other factors that we don't have access to that only the individual knows about. So I may have preferences for certain restaurants in the moment because I want to have a different experience, or I maybe think some friends might be there or whatever. You'll never know that about me. So really what I want in some sense is to be able to bid or be connected to the restaurants on the other side of the market. They'll look at me, I'll look at them. There will be essentially offers made, and I'll look at some particular restaurants on my cell phone in the app that have made an offer to me, and then I will accept one of those offers and they'll have made a transaction. So that's a matching market. Now it's at scale that we've never seen before in microeconomics. We're not used to millions or tens of millions of people connected to millions or hundreds of millions of entities, merchants or whatever. And similarly, drivers on one side, street segments on the other side. That's a matching market. And so if you value these things economically, you can start to actually see how that matching might be done. What's new here is that economists didn't typically talk about matching markets with data analysis. How much do I prefer a certain path to the airport? How much do I prefer certain restaurants? Well, I don't even know myself a priori. I have to have some experience in that. So I have to be a statistician analyzing my own data, starting to form my preferences in the context of what everyone else is doing, and perhaps sharing information. So whoever's building such a system, and they don't really exist that much, you can think of Uber as something like this. It matches drivers and riders, and it does use a modicum of data analysis, but just not very much, and it's not very effectual, at least certainly on one side of the market. But it has the flavor that I'm talking about. It's a data-oriented two-way market. So I think there'll be more and more of these things going forward. And my favorite example of this is music. So you'd think that we're in an era of, music, this is the world's best music market ever, because there's more music being made than ever before, and more people are listening to it than ever before. But there isn't a music market, really. There are a few famous musicians who are made super rich, and their music is promoted, but the long tail of most people is not in the market. And in fact, if you look at the data, 95% of the songs being listened to today in the US will be by artists you never heard of, and they're songs written in the last few months. So 95%. So everyone thinks that it's the famous musicians that we're all listening to, Beyonce or the Beatles or whatever, and that's just simply not true. And so a lot of the people making the music are, 16-year-olds who just do this as for fun on their laptop. They upload the songs. They're really good at it. People listen to the songs. They upload them to a site like SoundCloud, and then another site like Spotify will stream that to people. But now the market's gone. There's no connection between who wrote the song and made the song to who's listening to the song, and no transaction and no money. So there's no job available for the person who's actually providing economic value to all those people. Spotify makes a little bit of money because they created an artificial advertising market or a subscription market to make money for themselves, but they didn't create an actual market. So how do you create such a market? Should that be our job as statistical engineers? And I think, yes, it should be. This is a great example of something where a little bit of data analysis can go a long way. All right, and so in fact, it's not that hard to imagine doing this. So imagine that everyone who's a musician, meaning they uploaded some songs to some site like SoundCloud, is supplied with a dashboard at the end of the week. And the dashboard has a map on it of the United States. And every time one of your songs has been listened to, there's a dot on the map. So if you're reasonably popular, you'll see lots of dots. And it could be that you see that, my goodness, in Cleveland, Ohio, 10,000 people listened to my songs last week. For whatever reason, I'm popular there. Maybe someone liked my music and told their friends. And now there's economic value associated with that. If you contact the venue owners in Cleveland, will probably be aware of that. You're aware of it. You connect to the venue owners, and they say, "Well, come give a show here." And in fact, we even know who's listening to your music. Advertise to them that you're coming. You go there and give a show, and you make $20,000. And you do that 3 times during the year, and there's a salary for you. You're not becoming rich, but you have an actual salary. And the company that did this, it created a market, and they'd simply take a transaction fee. They don't have to do any advertising and so on. So you've created a market, and then markets become creative. So the musician can offer to go play at the wedding of someone who listened to their music, and for $10,000, and so on and so forth. So this exists actually already. The person there in the bottom right is named Steve Stout. He's an entrepreneur and kind of a brilliant person who conceived of a notion like this. United Masters is the company. You can go look at it on the web. It has 1 million musicians now that are active there. They didn't sign with record companies, but they signed with United Masters, and they retain their own songs, and their music is being listened to by for example, the NBA. If you go to the NBA website, you will hear music behind the clips, and that music is United Masters artists. So Steve here made the connection between the producer and the consumer. He helped make a market. So I was actually involved. Via a colleague, Steve and I connected up, and I helped talk about the design of a dashboard and the statistical engineering behind this company. So this is creating jobs for people. And you can imagine doing this not just in the US, but in Brazil, Africa, India, China. And you can imagine doing this for not just music, but for other kinds of entertainment or information flows. So I think this is actually a huge opportunity for anyone with a statistical engineering mindset. Again, the phrase AI is often being used for a lot of these kind of activities in industry. And there's a concern that AI is taking away jobs because it's kind of replicating what humans can do. This model is explicitly complementary. You're not doing what humans do, you're doing something complementary. You're connecting huge numbers of producers and consumers. That's something a computer can do, and you've added to human life. You, in fact, created more jobs. You didn't take away jobs. All right, so to do this as an engineering discipline, you have to take into account that you are creating markets here. and there's data and there's inferences and there's uncertainty about the market, and there may be robustness issues and so on. Are you creating a healthy market? Are you creating a damaging market? And so that's got to be part in scope for this emerging, let's call it discipline, if you will. All right, so some problems at the interface of statistical computing, whatever you want to call it, and econ. Multi-way markets in which individuals have to explore to learn their preferences. So exploration is a key part of decision side of learning. You don't know a priori what the right thing is. So in statistics, we don't talk a whole lot about it. We have bandit algorithms and there's A/B tests in industry. This is kind of where it comes out, but we don't have it in our curriculum very often to talk about the exploration side. We kind of wrap that into experimental design or something, but it's not really focused on, but it's critical in real life. Again, large-scale markets where you have to have some notion of a recommendation system, so information is shared among multiple people, because you can't have an experience of the entire market. You have to share information with like-minded people. Then all kinds of information sharing ideas, whether people are free riding or not, auctions where you learn preferences, and so on and so forth. In fact, privacy, fairness, and social good kind of issues are often talked about in the context of machine learning or statistical methods, but they have an economic side to them. You can't really talk about fairness until you talk about trade-offs and people's utilities and so on. All right, so the goal is to put all these things together in an academic discipline and make it relevant to industry. The last point is, just even apart from the statistical issues, that markets can be thought of as algorithms. They're making little local decisions and leading to a healthy functioning overall system, at least ideally. They're adaptive, they're robust, they can work at large scale and so on. So they're a powerful force that any engineering discipline should aspire to somehow making use of, corralling in some way, just like civil engineering may use of gravity. All right, and in fact, markets are not perfect. They have various failures. In the past, we've seen many market failures, and in the future, we'll have new kinds of markets based on statistics, and they will fail in new kinds of ways, and so we need to be thinking about that. All right, so the rest of my talk, I'm just going to give some vignettes of actual kind of research problems and proposed solutions to those problems to get a little bit of the flavor, again, of this bigger scope where you bring economics in contact with statistics, and then obviously algorithmic statistics. So the triad is present in all of these projects I'm going to be talking about. Okay, so let's go ahead and turn to that. So I may or may not get through all four of these. I really want to highlight a few points about each one of them. So I'm going to start with this problem of strategic classification. I have my students there, Tiana Zernich and Eric Mazumdar at Berkeley. All right, so classification is what you think it is. It's classifications is a terminology in statistics. Think of it as logistic regression with a binary response. But machine learning people use the phrase a lot too. You classify entities into one of two classes, good or bad, or true and false, and so on. So it's a high-dimensional, typically, problem where there's a large high-dimensional covariate and you're classifying entities into ones and zeros. All right, now we typically think of just gathering data, building a classifier, and then evaluating the classifier, and and so on and so forth. There's a pipeline of activity about how you structure the features, you use the covariates, how you measure the data, how you build it, how you validate it, and so on. And I'd argue that pipeline is missing a very, very key ingredient, which is that there's almost always feedback from the output to the input. Because the people who are involved in providing the data often are self-interested, and they have a vested interest in the outcome. If they see an outcome they don't like, they're going to change their data to get an outcome they might prefer. That happens all the time, and if we don't recognize it, we're building bad systems. So consider health insurance applications. Health insurance companies want to assess your state of health to be able to decide how much to charge you. There's of course regulatory constraints and so on, but there is a data gathering aspect to this. And so they're going to try to gather data that's not easy for you to falsify. If it's really just filling out a form, you could lie. And since you probably know that you should say certain things if you have a desired outcome, then you'll say those things and you'll get a desired outcome. You'll pay less for your health insurance. Of course, health insurance companies are aware of this, so they are going to try to make it harder for you to lie. They'll collect data that's a little bit harder for you just to fudge. So an example of that might be the health insurance company will say, um, if you could opt in to give access to the acceleration of your cell phone. So if your cell phone is accelerating a lot during the day over time, that means you're moving a lot, you're not sedentary. And that can be used as a covariate, if you will, to predict health outcomes. Right, so this actually happened, it happens. And it's a little bit hard for you to fake, but it's not that hard. So someone actually built a device you see on the right there. You stick your cell phone in it, and it moves the cell phone around in some random pattern all day long. And so the health insurance company thinks that you're exercising all day. It gives you a low score, a low price on your insurance. So you might think this is just silly, and more of this should be just ruled out as illegal or something. But you can't rule these things out. This is going to happen all the time in real life. It has to be part of the design of the system that's collecting this data and analyzing it. And this is called Goodhart's law in economics. It's well known. Here's an example of a poverty index score that was designed in 1994. On the upper left there, you see the score was well designed. You had a nice little Gaussian behavior there. But by 2003, it no longer looks Gaussian because people realized what was in the score, and they realized to make themselves appear more poor what to do, and people did that, and the whole distribution shifted over to the left in this very distinctly non-Gaussian way. So most people are now poor by this criterion, and of course, why do they want to be poor? Well, it's because they get more benefits in some sense. So this happens all the time. This is called Goodhart's law in economics, and I'd argue it's just extremely common. Here's another example of it. Uber drivers in Los Angeles. This was happened a few years ago. That Uber drivers colluded. They agreed that at Los Angeles airport at noon they would all turn off their cell phones. And as they turn off their cell phones, the pricing algorithm recognized there was not much supply, and it raised the price steadily over the next half hour. And 30 minutes later, everyone turned their cell phone back on, and they all got that high price and took the riders to the destination at the high price. And then this repeated from time to time. So, again, you could try to rule this out, make it illegal in some sense, or scold your drivers. But it's really just part of life. People are going to do this kind of thing all the time. All right, so good data science or statistical engineering should take this into account, and it's not just a data cleaning issue. It's not just bias. It's something deeper. All right, so it's really about feedback loops. You have strategic agents on one side who want a favorable prediction. You've got the decision maker who wants to minimize prediction loss. They interact via a data and model. So the strategists may in fact get to see the model because there may be regulatory reasons. If you're doing loan applications or health, you may have to publish the model, or you may have to at least tell what kind of model you're using. So people start to glean what they might do to adjust the data to get the outcome they prefer. And again, that's just going to be really part of life, and it has to be taken into account. So we have adaptation to each side of this. It is a market effectively. So the question becomes now not just what's the prediction error and how do you evaluate that, and what's the bias and all. It becomes what's the equilibrium solution, and is it a good equilibrium, and how is it achieved? Is it robust, and so on. All right, so this is a game. We're now in game theoretic land, and this has a name in game theory. This is a Stackelberg game, where Stackelberg is different from Nash equilibrium. Nash equilibrium are simultaneous games. Stackelberg are sequential games. One side makes a move, the other side responds to that move. And this is a repeated Stackelberg game. Now, who leads and who follows? And do you get what kind of results do you get depending on who leads and who follows? Well, that's interesting. So if you think of somehow the leader as having an advantage, they get to make the first move. But the follower gets to see your move and do the best thing based on your move. So sometimes they might have the advantage, but then the leader knows what you're going to do, or can predict what you're going to do. So they make their move and aware of that consequence. So it's not clear is the short answer. It depends, and you have to do analysis to think about this in particular situations. So in this situation, what's going to happen? Well, we've got a predictive model that's based on a parameter theta. We got data, let's call that, there's some measure mu, and mu and theta are the kind of the variables that are being adjusted here in this game. All right, so in step one, the decision maker announces a model. The strategic agents in step two observe the model, and they choose some measure over data. And it may cost them, there's some true data perhaps, and it may cost them a little bit to move their data. They have to pay money or do more exercise or whatever. And so that's part of the model as well, that cost. So for example, the decision maker announces a credit scoring system. People take a best response to that and try to improve their credit score. All right, so the game has dynamics in it where there's a theta vector and there's a best response. And the classical version of this is that there's one time scale, and the essential modeler responds quickest. The essential modeler is the leader, and all the strategic agents are the follower. So the strategic agents are responding as soon as a new model is announced quickly, and the essential modeler has got infinite resources, so they have the most updated model possible at every moment. Okay, but we realize that leads to one kind of Stackelberg equilibrium. But if you use different timescales, you can get different Stackelberg equilibria, and some of them might be preferable. So we should understand that. All right. So we talk about proactive and reactive decision makers. If the decision maker is slow relative to the agents, they update their model only very infrequently. We call that the proactive mode, and the decision maker can choose to be proactive in this way, or they can be reactive. Proactive models also occur in real life. For example, college admissions. The university does not change their model of admissions very often. Maybe every few years, they'll kind of adjust their criteria, and people best respond to whatever the criteria are over time. Whereas on the other hand, the reactive case is the decision maker is fast, and this is what happens, for example, in online platforms. The YouTube model or Uber or whatever is adjusted immediately based on the computing resources they have, and the strategic agents are slow relative to that. So we analyzed this kind of situation with with statistical models like logistic regression as the model, and found that in fact you get Stackelberg equilibria here. You do have equilibria. They're different equilibria depending on proactive versus reactive. And it turned out that the reactive case, this one here, where the decision maker is fast, leads to equilibria that the decision maker likes, and the strategic agents could not like. They can have very bad social burden here. All right. So you think, well, okay, maybe this is bad for, maybe the government should come in and regulate this because the decision maker is happy, but the people aren't. So you should maybe make them go back to this other model where the people are maybe happy and the decision maker's not. But it turns out that's not what the mathematics tells you. The mathematics tells you that other model actually leads to an equilibrium where both the strategic agents and the decision maker are happier. Okay, so this is actually somewhat of a surprise. It's a new result in game theory when you bring in the statistics. Both players prefer this equilibrium where the strategic agents lead. In other words, the humans are responding quickly. They're more like the college admissions model. You get better equilibrium both for the strategic agents and for the central decision maker. Okay, so that's all I wanted to say about that little research vignette, if you will. This is brand new results from this summer. There's going to be a lot more to do on this kind of problem. It really does have a game theory flavor here, but this is not the kind of game theory you'll find in game theory textbooks because we have logistic regression, we have data analysis, we have data collection, and kind of experimental design in the inner loop of the game theory. Okay, so I'm going to do another vignette. Looks like I got about maybe 10 minutes left in my talk here. If that's not true, please let me know. Work with Lydia Liu and Horia Mani at Berkeley. So again, we're going to be blending statistics and economics here. On the statistics side, we have competing bandits, or well, not just competing bandits, we have bandits. And on the economic side, we have matching markets. All right, so multi-arm bandits, presumably you all know what they are. They are really important in industry. They're, A/B tests are done with this. And again, we don't tend to teach this in our statistics curriculum, but it, of course, has in the 1950s, it was certainly studied and to this day, often in operations research, a little bit more than in statistics. Anyway, you have a number of options. An agent is trying to decide between the options, and each option has a reward associated with it. It's maybe stochastic, maybe adversarial. And you have to sample the different options and get the rewards to decide which of the choices is best. Okay, so these are unknown reward distributions, and you'd like to maximize maybe mean reward. So you have what's called an exploration exploitation trade-off, meaning that you'd like to pick the arm that has got the best reward and just do that all the time because you get high reward. On the other hand, you don't know a priori which is the best arms. You have to explore all the arms a little bit, but as you explore, you're not exploiting. So you have to blend exploration and exploitation. Okay, and so there are many algorithms that are known to be successful in this domain. One of the earlier ones is called upper confidence bound. It's very much a statistician's algorithm. So the agent forms a confidence interval on the mean reward for each of the arms based on the historical data. The algorithm then picks the arm that has got the maximal or highest upper confidence bound. So the upper confidence bound can be high for one of two reasons. One is because the overall distribution is shifted up and to the right. You have a high mean reward. It's a good arm. Or it could be that the upper confidence bound is high because you have a large uncertainty for that arm. In either case, you should pick that arm. In the first case, for exploitation reasons. In the second case, for exploration reasons. So anyway, if you pick this arm, you get an algorithm called the UCB algorithm. And the analysis of this is in terms of regret. Regret is measured relative to an oracle who knows the best arm a priori and always picks that arm. So the question is, how well do you do relative to that? And in the beginning, you'll not do very well, but over time you should get closer and closer. And the best regrets for this problem are known to be logarithmic in the time horizon. And in particular, UCB has logarithmic regret in this problem. All right, so that's the statistical decision-making problem. Now let's put that in contact with the economics problem of matching markets. So matching markets are also pretty famous and widely used in industry. Nobel Prizes have been given for matching markets. So here you have it's a bipartite graph, buyers on one side, sellers on the other. The buyers have a known preference ordering over the sellers, and the sellers have a known preference ordering over the buyers. So this is assumed known a priori. And then the algorithm attempts to do a match where everyone is matched, as well as possible, and that's defined by a notion of stability, that there are no pair of buyer and seller who'd prefer to be matched to someone else. And there's an algorithm that achieves this, in polynomial time, a kind of bidding algorithm. Okay, so the issue here is that you really want to put these two ideas together. In real life, I will not know my preference over a large number of options. Restaurants in Shanghai, I have no idea. Even college admissions, I really don't know my preference over all colleges. So there has to be, in some ways, an information gathering process where I maybe explore a little bit the options and learn about them, and that's part of the overall matching. So let's imagine we have now a matching market where there's multiple agents and they're all exploring like an abandoned algorithm. So the picture would look like this: competing agents. And now the question becomes, as they're exploring, if they pick different options, there's no problem. But what if they pick the same option? Well, in this model, there's scarcity. So you would have to sort of imagine maybe that one of the agents gets the reward and the other gets no reward. That model's congestion. So who gets the reward? Well, here the bear got the reward, and it's because arm 2 has its own preferences on the other side of the market. So arm 2 seems to prefer the bear. The human observes this and they realize, oh, I see, I like arm 2, but the bear does also. And when I pick arm 2, I tend to lose. So I better explore some of the other options more than I otherwise would. So competition seems to be leading to an increase in regret here. And the question is that really true? Can you analyze that? And what's a good algorithm for structuring this kind of statistical market? All right, so we've studied this and we call these things bandit markets. It's kind of what I've already said. And now to analyze this, you need to define a notion of regret. I don't want to get into the detailed notation here, but basically the oracle is that you assume you knew the preferences a priori, like in the classical case, and you did a Gales-Shapley matching. What is your regret relative to that as you're doing the learning? Okay, so we call that the stable regret. And we'd like to minimize this. All right, so we've studied a number of algorithms. Here's one particular algorithm. This is called Gale-Shapley upper confidence bound, and it's just is gluing together of the ideas I've already presented. So each agent has a confidence interval on each arm, and they send the upper confidence bound for each arm to Gale-Shapley algorithm. It runs and does a tentative matching, and then people get a reward from that matching and adjust their confidence intervals based on that matching, and the algorithm iterates. Okay, so this can be used in real life problems. Does it have good theoretical properties? And the answer is yes, it does. It has actually logarithmic regret. So the regret does go up a little bit, and that's because of this delta squared in the denominator. That's a measure of the overlap among the probabilities, the reward distributions. So if you have small overlap, you get a larger regret, which makes intuitive sense. But it's only a constant. The regret overall still scales in the time horizon as logarithmic in the time horizon. So this says that you can effectively learn in this multi-agent setting, and the overlap among agents does create competition, but it's only a constant. Okay, so that's the second problem that gives you a little bit of a flavor of statistical decision-making meets economics sort of setting. It's a little bit of a stylized problem, but it's kind of already generating a lot of research, and problems of this kind, statistical decision-making in multi-agent setting, I think are going to become more and more common because they reflect real-life considerations. I think I'll do this one more, and then I'm going to close up. So again, work with students at Berkeley. So auctions are a classical bit of microeconomics. You don't see a lot of them in statistics, but they are a data gathering mechanism. They try to gather this notion of a private valuation, that if you knew my valuation for things, you would probably give me a better service. At least you might give me the item I like. But I have this held privately. I don't want to just give you this data. So I want to use an auction to sort of reveal your preference without over revealing. Okay, so optimal auctions have been designed in economics. There are, again, Nobel Prizes given for this, and they're used in real life. They, again, aren't very statistical. They assume a priori, the auction designer knows a priori, not the valuation, but they know the distribution on the valuations. These are called Bayesian auctions. In real life, you don't know the distribution on the valuations probably. But in a repeated setting, you might be able to form an empirical estimate of that. And the question is, if you plug in that empirical estimate, you get a good auction. But the real question is, this is an adversarial situation. We have strategic agents. Probably we're not going to get out IID data. Probably they're going to shape their data to be different. And the question is, do you still get out an effective auction? Okay, so we have this question then of robust estimation or learning of an optimal auction. And the question is, can this even be done? And again, I'm not going to get into details. We have a paper on this that you can see on my website. But just to say we're able to do this. And so we have defined an empirical Meyerson auction that's putting together statistics with economics. Empirical just means we're using data, and Meyerson auction means we're using classical economic theory. And we're able to show that our version of it is robust. The classical empirical, the plug-in estimate is not. But we have a particular robustification that is robust to any distribution within alpha of the true distribution in KS distance. And let me just say a little bit more about what that means. Here's just briefly our model. Bidders have true evaluation distributions, D star, but samples are drawn from corrupted distributions, D tilde. And we assume that you're within an alpha factor in Kolmogorov-Smirnov distance, i.e. you can move arbitrarily the mass of the probability distribution up to a level alpha. So this is a pretty good model for an adversary. You can allow a complete change of the distribution up to level alpha. And here's a theorem that says your revenue from the auction is within a factor of 1 minus alpha of the revenue you would get out of the optimal auction. And at the bottom of the page there is a sample complexity. How many samples do you need to collect to achieve this level of performance in your auction? Okay, so this is really bringing together statistical inference ideas with auction design issues. Okay, I'm going to finish here. I think, there's an algorithm sketch here just to say this is the empirical auction it uses a lower convex envelope of a piecewise constant function. So there you're actually bringing in kind of, statistical ideas of how to estimate piecewise constant functions and so on. Okay, there was a last project which I've decided I'm not going to cover, but this has to do with back to kind of bandits and matching markets and quantifying equilibria here. So equilibria in economics is usually a binary notion. You're either stable or you're not. If you want to do statistics with things, you got to kind of turn those notions into something like a smooth curve you can optimize. And so we have a smooth notion of equilibrium. And so this paper with my students at Berkeley does this. So I'm going to skip that. Okay, so I'm going to finish just by returning to this slide, which I set up in the beginning, that this field that, again, if you want to call it statistical engineering, if you really want statistical engineering to have a very, very broad scope, it should be at least the scope that's being used for machine learning in industry. Meaning I take in data, I build large-scale systems, platforms that make services for people based on that, and I try to make guarantees the overall system behaves effectively for people. And so partly that's just kind of learning to make predictions and doing statistical analysis and having pipelines that do that, but partly it's putting that closed loop and multiple agents perspective into play so that you have economics as well. And I do believe this is the emerging phenomenon of the real world. It's very different than just sitting down with a scientist and analyzing their data, or looking at just a data set that someone in industry gave you and you had to analyze it and give back a plot of some kind. But I think this is the real engineering problem, is to design systems that do these kind of things. And again, returning to my slide about chemical engineering, someone who designs a chemical factory is not just designing one flow and one pipeline. They're designing the entire factory, and it has its feedback loops, it has its processes, it has its timescales, and it's the design of that factory which is the key, and not the design of just a single pipeline. All right, thanks very much for being an audience for me, and I look forward to further discussion today.
Thank you very much, Professor Jordan. That was really, really exciting, really insightful. We do have a couple questions here, so I'll just read one from the chat. This is from Christine Anderson-Cook. Her question is, in the vignettes that you shared, the goal seemed to be to find a single best solution with a clear winner. How easy is it to identify the winner in the context of several competing objectives for each participant? It seems like that might be a relatively common context.
No, absolutely. It's a great question, and that certainly would expand the scope of my talk by another hour. And so we have worked on that. We have kind of Pareto optimality kind of notions, but extensions of them for statistical purposes. So we also have notions of exchange economies and so on. So as I'm sure you're aware by asking the question, economists are definitely all over multi-objective kind of situations. And so partly we borrow their thinking, but we have to, again, adapt it to our setting. The problems do become harder, and often there is not just one answer. As you allude to, there might be trade-offs, and you want to reveal those trade-offs. So part of being a good system to me is not just that you optimize and you're done and it's a black box, but rather you're sort of transparent with the users. What are the options? What are the trade-offs? And you're also transparent about what everyone's getting out of it. So I want to participate in the system. I don't feel like I'm being treated badly. And in fact, this kind of word of equilibria, though, even though you're absolutely right, it's not itself enough. It's, I think, in many ways better than optimum. We often use the word optimal a lot in statistics. Optimal is often just unachievable, whereas equilibrium is maybe something a little more achievable. But as you point out, even softening that a little bit is important.
Excellent, thank you. So another question, you talked sort of about the synergy between combining different schools of thought and different disciplines, but I think our university curriculums don't really do that very well. And so I'm wondering what your thoughts are on how current statistical curricula need to change or adapt sort of in the response to these more modern problems that we're trying to solve.
Yeah, no, that's a great question also. So first of all, let me just, I didn't really mention David Blackwell here. So let me just say that, anyone with a little bit of gray hair, remembers some of these issues back in the day. And I got to know David Blackwell when I first came to Berkeley. None of what I talked about here would be a surprise to David Blackwell. He worked simultaneously in statistics and economics and computation. And there's Blackwell theorems in each of those fields. So I don't think he perceived a difference between these things. He already had this. And moreover, you know, the people of that era, Bellman or even von Neumann, et cetera, similarly, they were kind of mathematicians coming into game theory. Statistics was all part of the same, part and parcel of the same thing. So in that era, there was a unity in their thinking style, at least, and then it split apart. And somehow, you know, computation took just the programming language side, and you know, bits in the computer, and you know, economics took a certain set of things, and statistics took kind of linear regression. And yeah, but really, they should have been all together all the time, and they're having to come back together by the real world challenges. You know, so that said, you know, a few years ago, I got together with colleagues at Berkeley, and we designed a new program, a new undergraduate curriculum for data science, and it's had some impact. And me and the two colleagues that were most involved in the design, we wrote an article in the Harvard Data Science Review earlier this year. It's called Computational Thinking and Inferential Thinking, you know, Design of Data Science Curriculum at Berkeley. And I would point to that. I would love it if people here would read that. You know, that was before I had a lot of economics in my thinking, but by the end of the undergraduate sequence, you arrive at economics and game theory and matching. But anyway, it starts with you know, a very computational view of statistics, that, you know, permutation tests and bootstraps and all are highlighted, and asymptotics are not. So you learn, for example, the inferential problem is to compare two columns of numbers. The approach is going to be to you know, put them together in a big column and do a permutation and then get a sampling distribution. And you can learn to program that in your favorite programming language, Python or whatever. So we teach them the Python, we teach them the permutation test, we show the histograms, and then we work on real data, and then we move to another little vignette, if you will. That's in the freshman level. So that was the design of that class, and students loved it. We get, you know, now nearly 2,000, or actually up to 3,000 students a year taking this class at Berkeley. And it doesn't do a lot of mathematics, but there's mathematical concepts pervading it. There's real data analysis, and they're doing engineering kind of building of things. And by the time they get through the curriculum, they've built bigger systems, and they've learned a lot more inferential principles. So to me, that doing that at the undergrad level was actually eye-opening and revealing. You don't have to just try to take all of statistics and blend it with all of computer science. You throw away a fair amount of the older part of statistics. In fact, a lot of the asymptotics is not really relevant. You replace it with the computer does the computation, and you get a win-win. You can now teach the more advanced methods at the freshman level, and students actually like it because they can deploy it themselves. And I do think that the econ thing is not that hard to bring in as well. Like a matching market's a nice little cute algorithm. You can teach that as well. So long story short, I think at the undergraduate level, a lot of us can and should cast aside and redeploy a brand new curriculum there. And that requires buy-in and lots of effort. We did that at Berkeley, where it's still a work in progress. But I think that's what's needed. And the grad level, I mean, I just think a lot of the students already get this, and just kind of, you know, open up the curriculum and let them take courses in computer science and economics, let them blend it in their own way. But I think the undergrad curriculum is, so data science helped get leverage on this, and I think maybe that's still a good terminology going forward. You know, but I would just sort of blend in a little bit of the econ, and I think you're kind of good to go.
Yeah, great, thank you. Well, I see there's a couple other questions, but I want to respect your time. We have a panel discussion coming up in 5 minutes that you're also a part of, so I want to give you a chance to have a break. I think those of you who did ask questions that weren't answered, I'm sure Dr. Jordan would be happy to respond to them by email later at some point, or if we have time later in the program, we can maybe come back to it. But for now, I just want to thank you on behalf of all of us in the audience, Dr. Jordan, for your talk and for your time. So with that said, let's spend the next 5 minutes or so having a quick break. At 11:10, we're going to come back with the panel discussion where we address the past, present, and future of statistical engineering. Thanks, everybody. All right, well, it's 10 after 11 now, so I think it's time to get started. And I don't want to spend too much time here introducing everyone. Everyone here is very esteemed, very well known, but we want to get into the discussion. So let me just go quickly. Moderating this discussion is Roger Hurrell, the Bright Peschel Associate Professor for Statistics at Union College, and he's also the past chair of ISEA. We have Christine Anderson Cook, retired research scientist from Los Alamos National Laboratory. We have Stefan Steiner from the University of Waterloo, who you met earlier today. We have Dick DeVoe, who is the C. Carlisle and Margaret Tippett Professor of Statistics at Williams College, Diego Cuonan, Professor of Data Science at the University of Geneva and CEO of Statu Consulting. We have Allison Jones-Farmer, who's the Van Andel Professor of Business Analytics at Miami University. Jeroen de Mast, who is Academic Director at the Euronymous Academy of Data Science and Scientific Director at Holland Innovative. And lastly, we have, of course, Dr. Michael Jordan from Berkeley, who was just our keynote speaker. So without further ado, I'll let Roger take this away and moderate this discussion.
Great, thanks so much, Nathaniel. We are going to talk about the past, present, and future of statistical engineering. So it makes sense to start with the past. And as most of you know, but probably not all of you, in 2012, the journal Quality Engineering had a special edition on statistical engineering. Actually, Christine Anderson Cook was one of the co-editors of that. So my first question is, how has statistical engineering evolved since this 2012 publication? What has helped or hindered its development as a unique discipline? And I'm going to ask Allison if she would start the discussion on this question.
Sure, I'm happy to. First of all, thank you, Roger. I want to thank the planning committee for organizing this and for inviting me to be a part of the panel. I want to thank you for coordinating a hopefully organized panel session. It was fun for me to look back at the 2012 publication because I haven't read it in almost 10 years. There's a few obvious things that I want to start out with. There's really 5 major points that I want to make, and I want to make them really quickly. Number one, the movement has just really changed and grown since the writing of that. At the time, you described statistical engineering as the study of, right? And I think the most telling change was recommended in that journal, and that was to change it to the discipline of. And I think that's been a huge and profound change in terms of developing statistical engineering. And from that, there's just really a lot of growth that's happened in terms of the founding of ISEA. You know, we have 556 members, I heard of, as of this morning. And just a lot of people have really refined the mission, and the community has just really grown. And so that's, I think, a testament to the leadership in this organization that really pulled this together. There's really 4 other things I want to talk about, though. The next thing is really the world has changed. The world has changed tremendously in the last 10 years, and that has precipitated, I think, more of a need for a discipline like statistical engineering. So I pulled the Gartner hype cycles for 2012 just to kind of see where we were from an emerging technology standpoint back then. And it was comical to read that these were the things that were on the horizon for 10 years from now. And if you try to put yourself back 10 years ago, I'm not sure that we really understood how these things would change our world. So it was things like 3D printing, Internet of Things, mobile robots, big data, gamification, wireless technology, natural language processing, private clouds, home health monitoring, and internet TV. And you can see all of those are part of our world today, and those were not 10 years ago. That's made a huge difference. If you look at the same emerging technology hype cycle today, the things that are on there are quantum machine learning, AI-driven innovation, AI augmented design, physics-informed AI, non-fungible tokens, decentralized finance, and the list goes on. You might have to Google some of these things to really understand what they are at this time, but 10 years from now, we're going to be in an even very different place from a technology standpoint. All of this has really changed the culture and the need for really interdisciplinary problem solving. So then the third thing I want to mention is that our enabling tools, our enabling technologies have really changed tremendously in terms of the ability to solve problems and solve them well. Some things that are really important in the development is readable code. Things that tools we have now are things like our Markdown, Jupyter notebooks, where we can have code and problem solving and output and text integrated together for better problem solving. We have shared documents like the Google Suite, Share LaTeX. We have cloud computing. We have web-based conferencing that's become part of our culture, and GitHub communication, file sharing. It allows us to solve problems better. And then all of this new technology, all of this new data brings together sort of this world of complex problems that need to be solved, and some very prominent failures in solving those complex problems that have made it to mainstream media. And so this has really precipitated the need for an organization like statistical engineering, where we're interdisciplinary and we're focused on solving a problem from the start to the finish, not just in one pipeline. So I'm going to end that with my comments on this particular question of where we come as a discipline and really as a world. So it's not so historically focused, but it's really future focused on the evolution and the future.
Great, thank you very much. I'm going to open up the floor to the other panelists to see if others have comments.
Yeah, then maybe I'll take on the role of asking critical questions simply to have a bit of a discussion. So you say the world has changed a lot. Somewhere earlier this morning in Lynn's presentation of the handbook, they talked a bit about the p-value controversy. I strongly believe that a lot of the statistical methods have also evolved. Last couple of decades have seen a flood of new analytical methods. In how far did the statistical engineering community grow with all these developments? And taking, for example, the statistical handbook as a point of reference, in how far did also the statistical engineering handbook leave 20th century analytics behind and fully embrace 21st century analytics? I'm playing a bit of the role of devil's advocate here, so just to have some discussion.
Is that for me? Like how? So if I understood how well you're asking me specifically how well the statistical engineering handbook addressed the progress in statistical methods, is that correct? I think it's limited, I'll be honest with you. I think that there's much more from a discipline not only in statistics, but in machine learning and in some of the enabling technologies that could have been included in that handbook, and hopefully will be included in future versions.
So I'll jump in and say that the way I capture a lot of this is that there's just a growing expectation of complexity. And so I think we have to feel nimble to respond to that expectation of, multiple data sources coming together, of sort of a really tailored solution to individual problems where, I think if we look back 10 years, sort of more of the stock solution felt like it was a good way to go. And so I think that nimbleness feels like something that we just really need to embrace and be ready for. And that to me is one of my reflections looking back at 10 years. And Alison, it was wonderful to hear the list of things that, we thought were like leading edge in 10 years from now. And now they're just like standard fare and an expectation. And that feels like something that we really have to, if we're going to stay relevant, we really have to be thinking in terms of being responsive, and this, realism and complexity now are sort of here to stay as an expectation.
Yeah, I agree with you, Christine. And I think that, 10 years ago, I was building programs in analytics, and because we were preparing for this data economy, which came very rapidly and is here. And now everything we're doing is just table stakes. And I work with my colleagues and I tell them that if we develop a new curriculum, it's really got a 5-year life cycle on it, because what we're going to be doing in 5 years is not what we're doing today. And I think that's an important message for the statistical engineering community as well. And I think it's also an important message that when I meet with chief data scientists and CEOs, which I do quite frequently in my role, they're always concerned with how we can get better problem solvers on their staff. And then they all have their own sort of methodology for problem solving. And some of them are loosely based on things we're familiar with. And some are quite intricate and in depth. But everybody seems to be searching for the best way to do this. And I'm not sure that there's one prescriptive method. But I think we all agree that we need to holistically solve problems and do a better job of that, and integrate a lot of different disciplines.
Dick.
Yeah, thanks. I don't know if there's a hand raise button like on Zoom, but I couldn't find it. I just did it. Yeah, I did it the old-fashioned way. So, all right, Jerome thought he was going to be controversial. I'll be even more of a devil's advocate here. Why hasn't this, what are the impediments to this succeeding? Well, Mike was really complimentary, being the outsider here. He said statistical engineering is great. I think the name is a disaster.
I agree.
I think we've got two things that people don't like at all. That is statistics and engineering, and you put them together. And now I understand the mindset. It sounds great, but look, we've got 39 people watching. We should have 3,900. And if we marketed this differently, I can't remember if it was Christine or Allison who just said holistic something or other. Roger and I and Ron and Paul Bellman have a paper coming out soon called Holistic Data Science Education. I think we need to wrap ourselves. I mean, Michael talked about machine learning, data science, blah, blah, blah. Unfortunately, these names are important. And as Mike pointed out, people just call it AI. I mean, I listened to an NPR story about how AI was saving the tigers. And I thought, okay, I got to listen to this. What they do is collect data and did logistic regression, and that's AI saving the tigers. So it reminds me a little about Taguchi methods back in the 80s when, I was with George Box and Stu Hunter. They were all up in arms about how Taguchi was taking over and claiming that he had invented all of orthogonal arrays. And Stu wrote an op-ed piece to the New York Times. But the point was, we have to use whatever it is. So I taught a course at Hewlett-Packard called Taguchi Design, and then I just taught DOE. And everybody was thrilled. So, I just think we need to think hard about statistical engineering as a name.
Dick, I'm going to agree with you, and I don't want to hog the question, but I'm in a business school, and I teach 9 hours in a master's program of what you would all consider statistical engineering, and there's no way I would ever call it statistical engineering because no one would take the class. And our companies that hire our students wouldn't know what it was or care, right? And so we've named it differently. And so,
what have you named it, Allison, if I may ask?
Well, I've got different parts of it, but the first 3 hours is called communicating with data, which is not a storytelling program, process. That's about appropriately scoping a problem, building a workflow, understanding the business value of what you're delivering, then building a solution, then talking about it in the end, right? But my philosophy is you can't communicate something if you don't have something worth communicating, and it has to deliver value to who you're presenting it to. So that's the first 3 hours of the program, and then we have experiential projects where the students work with real data, real clients. In the next, it's another 2-course sequence. So and we call that the business analytics practicum, which is not very sexily named either. So I don't know what to call it. So Dick, I wanted to say this point, but I don't have an alternative. And you were braver than I was. So thank you for that.
Okay, on that note, we are going to move on. I want to go to the next question, and I'm going to try to show a PowerPoint. Are people seeing a PowerPoint?
They are.
Good. So this is a PowerPoint that our keynote speaker, Michael, presented at the University of Michigan at a symposium on statistics in the data science era. I'll give everybody about 10 seconds to read it. And I want to get a dialogue around this particular slide. I'm going to ask Christine first. Fundamentally, do you agree or disagree with the main points that Michael has made in this slide, connecting engineering to problem solving? What do you think, Christine?
So absolutely, and I think in Michael's keynote talk, he also said it's beyond problem solving, it's also decision making. So I think of those as sort of the 2 main prongs of what we're attempting to tackle. And then I guess the spirit of the rest of the slide feels a bit pessimistic, that the majority of statisticians really view themselves as scientists and not so much in the realm of problem solvers or engineers. And so I'll say I've always been an outlier, if that's the prevalent view, that the reason I got into statistics was to work collaboratively with people and to solve problems and to sort of move the needle in other disciplines. And I guess the notion that statistics started with a science base, I don't agree with. If you look at the founding fathers, so George Box and Gossett and Uden and Fisher, you know, they were all embedded in the real world. And I think they were tackling hard problems and trying to, you know, interact with other disciplines to sort of make a difference. And so, you know, how did we get to this point where the science perspective of statistics seems to be the dominant one? I guess, you know, lots of academics with pressure to publish, that sort of has translated into, you know, create a new tool, publish a paper. And that feels unfortunate. And a microcosm of that is, I think, when, you know, you talk to students going into statistics, so either undergrads or grad students, you know, I think a lot of times when you say, well, why did you choose this? They'll say, I want to use statistics because I'm interested in problems in economics or in physics or in chemistry. And I think that will be useful. And certainly interns, you know, they write an essay now of why they want to get into grad school and what they're hoping to accomplish. And I think a lot of times it has that flavor, and then we say, well, rewrite this and say you're interested in tools. And that feels unfortunate. So I think that, you know, we can push and sort of, you know, right from the start, encourage both the problem solving and the tools and just restore that balance. And that actually will have, you know, the desired consequence. And you know, what I feel, and actually the reason I'm a statistician is Jacques Mackay at University of Waterloo gave a presentation, you know, come be a statistician. And what he did was he just described a whole bunch of problems that he was working on, and they were very interdisciplinary. And he said, you know, this is what you can do all day long as a statistician. And that was very appealing. And, you know, I think we just have to tell that message, and it's there and the students are drawn to it. I think we just turn it into a tools discussion, and that sort of makes everyone think science and truth and that sort of thing, when, you know, the natural inclination is there. So, you know, I'm much more optimistic that this is a change in perspective that we've sort of manufactured as a problem, as opposed to one that's intrinsically there historically. And, you know, the students that are drawn to statistics are probably not far from embracing this the way that we want them to.
Great, thank you. I'm going to stop sharing just so we can see the panelists again. I think everybody got a chance to see the slide. So I want to open up the floor to others.
And maybe a thought here. My school on data science is actually a joint venture between a business school and an engineering school. And of course, business schools and engineering schools have quite different research traditions. And that created some tension, some envy, some, let's say, snobbery. And one way they try to solve it is by simply giving appropriate names to different research traditions. So my school now recognizes that there's something that they call the explanatory sciences, which are like physics and biology. And what the explanatory sciences are after is truth finding. They want to explain things and find truth. There's also the formal sciences like mathematics and logic. What they are after is developing logical frameworks for reasoning. And they're not so much about truth finding, but about finding logical consistency. Where data science fits in is, as what I call at my school, a design science. And design science is modeled as engineering. So the typical examples that they give of design sciences are engineering, medicine, management. And in design sciences, the purpose is not so much explain stuff, but to discover actionable knowledge, techniques, methods, tools. And the criterion is not whether you found the truth, but whether the techniques or the frameworks that you come up with, whether they work. And so effectiveness, does it work? And simply by discerning these three of scientific academic endeavors and acknowledging that they have different goals and acknowledging that they have different traditions and ways in which they publish, for example, that helps a lot in my school.
Mm-hmm. Thank you. Others? Dick.
So I think we shouldn't be quite so pessimistic about all this. I think, we know what happened to statistics after World War II is that statistics tried to be a discipline. And so to be that in academics, it had to be mathy. And so people proved a lot of theorems and got tenure, and that was great. But if you look at statistics now, you can be a statistician even in academics without just doing asymptotics. You can do lots of cool computational applied work. In fact, the COPS Award 2 years ago was given to Hadley Whitcomb, and there's not a theorem around Hadley. I mean, his contributions are all computational, and that's the first time that happened. So I think we are evolving. I think these programs in data science, there's that one at Berkeley. I helped write some guidelines for undergraduate curriculum at Park City a few years ago with Deb Nolan and Rob Gould and a bunch of computer scientists. And I think we're trying to move towards that, but statistics as a science is still going to be there, right? I mean, that's part of it. We're not saying that should go away, right? We're saying there should be another discipline that does applied statistics in a large data set, computationally aware, economically aware, holistic way, and whatever that is. And I think they can exist side by side. I mean, we're trying to do that. And then you add trying to make it accessible to people who don't have all the math skills. There are tons of people out there who want to be part of data science and statistics who have not taken 3 semesters of calculus when they get to undergraduate. And we're working on that. That's a huge challenge too. I'm calling on my math colleagues to write something that crams those 6 semesters of math that you need into 2 semesters. And I'm still waiting, but I remain optimistic.
The perpetual optimist. Well, I'm going to use moderator's privilege and make a comment. If you look at the vast majority of statistics textbooks that exist today, I would argue that they're organized by tool. You've got a section on regression, you've got a section on time series, you've got a section on DOE, you've got a section on this. And what I think this slide was talking about, and Michael, I'm going to call on you in a minute. I think what this slide is talking about is the tools are the hows, not the what, if you want to be an engineer. In engineering, if you look at the disciplines of engineering, they're not organized around tools. So civil engineers build bridges, they design buildings. That's the problem that they work on. Now, what tools do they use? Well, there's a whole bunch of tools they use, but they're focused on what the problem is that they're trying to solve. Michael even talked about chemical engineers. Fundamentally, what they're doing is designing a chemical plant. So I like the slide because I do think our thinking as a community, the statistics community, is too oriented around individual tools and not oriented enough around what are the actual problems that we're trying to solve. So with that, Michael, I'm going to call on you. You actually prepared this slide. What are your thoughts looking back on it a couple years later?
Yeah, well, thanks. I agreed with all the comments here. Let me just amplify a couple of them. I do think the word design is a useful thing to have here. And the word building, making buildings, constructing artifacts that exist in the real world is kind of really the core of what Speed talked about here. So we've mostly been on the analysis side as statisticians. We analyze, right? We break down, and at the end of it, there's a paper or a table or whatever. But there should be an aspiration towards artifacts that exist in the real world that people use. And in fact, so computer science is oddly named science, right? Because these names are, terrible. But the core of it is a builder mentality, that your goal is to build an artifact that's actually used in real life. If you don't do that, that's not the core of computer science. There's sides, there's certain formal sides of it, all that, but that's the core. So, and this is what you asked to do if you're a statistician going into industry, right? Often you're asked to say, okay, we're designing a new system that will help allocate cars to, if you're Uber, cars to the city. and it takes in a bunch of data and it makes, geographical assumptions and all that. But at the end of the day, it makes actual allocation decisions. And a statistician is sort of associated with that project, but they should sort of own that project. That should be, I know the design principles here. I know how to make sure the tail is handled and so on. You see that some of this in hedge funds, where kind of a statistician will own the problem of analyzing this kind of commodity data and making sure that we make good trading decisions at the end of the day. You see a lot of role of statisticians there. But all these other kind of consumer-facing or real-world-facing industries, it's not just that we're applied, we don't actually deliver the artifact at the end. Yeah, we engaged, but it should be more. We should actually own the fact that we delivered the final product. And inferential and concerns and how to design inferential is kind of the right thing. One last comment about engineering. I totally agree with Dick, and I think I like to be provocative, as you can see from this slide, and so I was just comparing how the word engineering has gotten deprecated. Social science sounds really good. Social engineering sounds terrible. Genome science sounds great. Genome engineering sounds a bit dubious. And you could talk about mathematical sciences. That sounds great. Mathematical engineering sounds dull, and so on and so forth. So it's a bigger phenomenon in our intellectual landscape over the last 100 years that somehow this wonderful word engineering that comes from engin, French, right, that built things, has gotten completely deprecated. And so one could just choose to fight that, and I kind of like to do that in a provocative way, but I don't think it's a good idea for a group of people, 39 people, to fight that bigger battle. So I would own some of these other terms like design and data science, and own a chunk of them. Use the word inference a lot because a lot of people don't know what it means. You get to own that one. Design for inference, terms like that, and throw those around a little bit more. But anyway, that's enough comments about that, but thank you.
Well, I'm going to go to Stefan next because he hasn't made any comments. If I have time, I'll get back to you, Dick. Go ahead, Stefan.
Yeah, I just wanted to add something to the comments you made, Roger, about, I like the idea of starting with the problem and not worrying too much about the tools. One challenge I think we have as statisticians, though, is that we tend to, I don't know what you want to say, play in everyone's backyard. So the context within which, what kind of problems we work on can be very vast. So it's not quite as easy maybe as in civil engineering or some of the disciplines like that, to make it clear what the problems are and what the commonalities are among the problems that we're working on. And so that is certainly a challenge that we face. And I think maybe the framework that we developed for statistical engineering in the handbook is one way of sort of addressing sort of a broad range of problems, but it is a challenge, I think.
Great. Thank Dick. If you have a quick one.
Yeah, I have a quick one. A couple of comments. First, it's ironic that I actually have an undergraduate degree in civil engineering. I don't know how many of the other panelists have a degree in engineering, but I was saying all this, and yet I survived 4 years of that at least. I also want a little pushback about all this complaining about textbooks. There are some damn good ones out there that have this modern point of view. I have a whole shelf full of them. I won't mention any of the names or authors, but there are good ones that are not all the ones from the 70s that we hated, that are full of theorems and asymptotics. There's some really good modern ones out there. So let's stop dumping on all the textbooks.
And Dick wrote one of them.
He's written quite a few, not just one.
Well, you used the one, we used the one for our introductory classes that you wrote, Dick. So.
Okay, moving right along. I started my career at DuPont and then went to Hercules. So I had some background in chemistry and chemical engineering. And one of the interesting conversations I had by some old-time engineers who are no longer with us, is they pointed out that chemical engineering as a term and as a discipline was not well received initially. That the chemists didn't like it because they thought somebody else was grabbing some of their turf. They thought as chemists they owned anything that had to do with chemistry. And conversely, the mechanical engineers, electrical engineers, etc., didn't really like a new engineering discipline based on chemistry when traditionally engineering is based more on physics than any other science. So in the interest of an elevator speech, how would you briefly explain to skeptics the need for statistical engineering, whatever we might want to call it, And I'm going to call on Jeroen to go first for this one. And Nathaniel, he does need to be able to present. If you could switch over to him, please.
Yeah, sorry for that. That's because half my career I have worked as a consultant. So I think and communicate in terms of PowerPoint slides. Let's see. Can you see my screen? And I'm also wondering which screen you're seeing now.
So
It says past, present, and future of statistical engineering.
That sounds good. You see my slides now or my notes?
They're in presentation mode, so you might want to go to display settings and duplicate. There you go.
That's better. Yeah, so an elevator pitch, or rather, I would try to explain the value of statistical engineering. So I try to describe it in the form of a value proposition. I think that the word complex problem solving, that stands out on ISEA's documents and ISEA's website. So it's very central to the value proposition of statistical engineering, and I quite like it. For one, because the World Economic Forum, they publish every 5 years, the World Economic Forum publishes the Future of Jobs report, in which they describe what future generations should master. And complex problem solving is always listed as one of the essential skills that the current generations should master. So I quite like that complex problem solving is quite central to what statistical engineering is about. Now, if I listen to the students that I work with, and my students are executives, managers, professionals, then they typically say, okay, problem solving, I have data, or even better, I think I have big data and I know how to apply machine learning, or even better, I know how to apply deep learning. Maybe people versed in more traditional statistics will say, I believe that design of experiments is a very powerful tool, or maybe we need some control charts. And this is the perspective that Roger, just a few minutes ago, I believe, described as being tool-oriented. And the funny thing is that typically in 99% of the problems that my students work on, this is not a real challenge. We know how to apply machine learning. We know how to train deep learning. The real issues, the real challenges are in questions like these: how to translate a wordy and messy issue into a well-defined problem, or how to make sure that the algorithm or the model is reliable, that it doesn't have a bias. How to combine analytics with domain knowledge, how to collect data, or what sort of data do I need? When do I need experimental data? When can I get away with observational data, for example? Or how to get things done in a complex organization. And these are the much harder issues that solving complex problems involves. I think that's exactly the value that statistical engineering has to offer, and I've tried to capture that in this one sentence here. Statistical engineering is about the sound application of data-driven analytics for complex problem solving. Where problem solving is as opposed to this focus on tools, because problem solving puts the focus on the process of problem solving from beginning to end, from structuring a problem into a well-structured problem that you can actually solve using analytics, all the way down to the implementation of a solution and dealing with organizational complexity. I believe statistical engineering is about data-driven analytics, as opposed to, for example, much of what they do in business analytics, where they derive models from first principles, from the laws of probability, from combinatorics. I think that sets statistical engineering apart, is that we work with data-driven models. The sound application is a very important aspect, because that makes statistical engineering go beyond algorithmics. It's the inferential part. I also very much like the word inference. It's questions like, what sort of a model do I need? Do I need an explanatory causal model, or do I need a predictive model? And what is appropriate data? How do I make sure that my training data are a representative sample? How to manage uncertainty predictions. I think that there's a lot here where statistical engineering has a lot of value to put to the table that people who come from a more algorithmic background don't have. And Lynn emphasized this earlier this morning, statistical engineering is a lot about the doing of statistics. It's about applying statistics. And that means that our community doesn't accept what I've referred to here as the normal IID mindset, where we make assumptions for the methods that we use. Stereotypically the normal IID assumption, and then when the assumptions are violated, that's the end of it. We blame it on the data. I cannot use these data, they aren't normal IID. I believe what really adds a lot of value in the way our community is more accustomed to work is that we accept that in applying analytics, you will encounter a lot of complications, like outliers, like non-normal data, like data that aren't IID. And we don't shy away from that sort of complications. Rather, we try to come up with a sound solution. So the sound application of data-driven analytics for complex problem solving. I want to add one final thought. In my school, we offer data science programs to professionals and executives, and many of them actually have a background in Six Sigma, like many of us in our community also have. And I observed that professionals with, for example, a Six Sigma black belt training, they have a head start on the learning curve. And of course, also Six Sigma black belts, we need to teach them a thing or two. I believe that we need to teach them what modern 21st century data infrastructures look like. And I believe that also the Six Sigma community should adopt more modern analytics. But that's all in this part. The tool-focused part, and I believe that is the easy part to learn. The more challenging part to learn is the more relevant questions that are pointed out. And I note that people with a background in Six Sigma, they have a head start in that department. And I believe that's also true for the statistical engineering community.
Great. Thank
That's
you.
my point. Now I need to find out how to stop sharing my screen. Nathaniel, can you help me there?
So I'm going to open up the floor for others to comment on this question. Christine.
So I think that's a wonderful organization of things, and just to connect to some things that Michael talked about in his keynote talk, I think there's also complex decision making that I would like to add to that, right? So think of the example of the medical decision that a person is confronted with. All of those issues of the quality of the data and how connected it is to my decision. Like I think there's a little bubble similar to what you had for the decision making piece that highlights all of those sort of connection to reality of how do I use this data to help the decision that has consequences for me and for my organization. That I think I'd like to see that added to your little nugget of the definition of things that we're tackling. But I really like the organization.
Allison.
Yeah, I also enjoyed the presentation, and I want to kind of just share a slightly different perspective. Well, maybe not different, but complementary perspective. But you did mention that business analytics was not data-driven analytics, and I would disagree with that term completely.
Let me correct, Alison. I actually said that a lot of the models that are using business analytics aren't data-driven. Some
well,
are.
I think it depends on your program. So we can talk about that offline. But we teach data-driven analytics in our university. The second thing I will say is I mentioned earlier that I have a lot of industry involvement, and largely that's because we work with industry both in a consulting realm, but also in terms of preparing students for the workforce. That's what our programs are focused on, both at the undergraduate and the graduate level. And we have built these sort of from the ground up to be holistic. And what we do is we hire not only statisticians, actually we only have 3 statisticians on our faculty, and I'm one of them, and the remainder are computer scientists and engineers. And we've specifically hired them, including a systems engineer, that works with us in helping to prepare the students in terms of model deployment. And we focus on a product-based analytics solution process where we teach the students that they're building an analytics product to solve a particular problem. So from that standpoint, I've never once talked to a company or a hiring manager that has said, I want your student to be able to, fit a neural net. I've never once have they said they need to know how to, build this specific type of model. And they don't even particularly care what language that they code in. What they consistently say is we want them to be able to solve problems. We want them to be able to solve problems that we can actually use. And so that's why I think this organization's onto something. And so I think I agree with your elevator pitch, if you were. But I hope that we can make it a broader community because I think that there's a real need.
Okay, I'm going to move on because I do want to save some time at the end for questions from the floor. So the next question relates to a comment that several of you have made, including Michael in his keynote. The world is inundated with terms for database methodologies, often used interchangeably by the media. Terms such as big data analytics, machine learning, AI, data science, business analytics, statistical learning. We could probably come up with a few more. We certainly don't need another buzzword. So what do you see as the unique niche of statistical engineering among all these terms? And I'm going to ask Diego if he'd lead the conversation on this one.
So great to be with you. And I didn't want to comment on the previous point. I wanted to resemble everything in this question here. And I see this always depends what you mean by the different term, whether business analytics here, this and this. And maybe just add one important point also with respect to my journey. So 20 years ago, I received a PhD in statistics, and I directly started my own consulting company 20 years ago because I was inspired by statistical thinking. I read all the stuff. Then came statistical engineering. So I read all this stuff. And I also learned over 20 years how to sell this thing, let's call it now, on place statistical engineering. And it's fully, in some point in agreement, was Sharon put on the table. Is really coming back to the point we started the discussion is, it's really the engineering. This is for us, this is clear that this is statistical engineering. This is how it's working. This is the engineering mindset. And from the beginning on, when I started about always speaking with clients, also government, the private sector, I always want to get them the statistical engineering mindset in their head. And I was very difficult to market the word statistical engineering. But what was easy to do is something which was put at some point previously is this, hey guys, this is data-driven problem solving, even not using the word analytics. And why we want to solve problems? Because we want to enable data-informed decision-making. We want to enable continuous improvement. So it's a very simplistic notion. Okay, the focus is on the problem. And like an engineer, you think about what tools can be used. And as such, for me, for example, things you mentioned, Roger, like big data analytics, machine learning, AI technologies, data science, business analytics, statistical learning, it's call what you want, are potential tools which I could use from an engineering point once I have clearly defined the problem, which is complex, which is unstructured, where I need to have the good skills. And I then decide which tools out of the arsenal of all tools which exist do I put together for this project. And what also clear is, and this is really the unique niche can be played putting a little bit more focus on something which is very important. There's no perfect solution to a problem. And really have what's, I think in the industry, you have this minimal viable product idea. And this, you have like a minimal viable solution to a problem. This also means for whom is it a problem? And this is something which it's not directly linked. What Michael had, this idea of a market. A market is working if you have consumers and you have producers. So if we do solutions, they have to be for someone. So this is really this minimal viable solution idea was really a little bit, this is it's like an engineer, you try it out, you do it very fast, and you want to prepare to fail, and you learn out of it. And this is really this continuous improvement thing which goes on. So I think at some point, it has a very unique need, putting all other things together. And now I agree, there's a little bit of marketing our community is missing. And maybe also there's a misnomer with the word. I once read something about the history about SPC, statistical process control, that this is a misnomer. It's more like process aided by statistical techniques. So here it's more like engineering aided by statistical thinking, but then we have to explain what's meant by statistical thinking. So to avoid all this, even if we have really this idea of, I think, this sound application of data-driven problem solving to enable data-informed decision-making and enable continuous improvement. So there is a unique place here to find, but for this, we need marketing, and very good marketing, and not fighting against the other terms which are taken by communities, but to tell them, hey guys, this is interdisciplinary. This is team sport, so we need you, we can help you, and collaborative, maybe there's something wonderful also for the society who comes in. So there's a unique niche, I think, without overcoming the fight, okay, is it business analytics or not? Because this is my second hat, I created a master in business analytics in Geneva, and what I train are statistical engineers. And business analytics is exactly the way statistical thinking is about solving complex, unstructured, data-rich problems to enable this data-informed decision-making. This is how I defined business analytics. So now we have here in the call 3 different definitions, so it will be very difficult to match. So I think coming to this point, there's a unique niche, and maybe we may need some marketing help, how to get hear our voices.
Thank you. I'm going to open up the discussion to the rest of the panel now. Any other comments? Stefan.
Yeah, one other thing I would add is that one of the niches I think that statistical engineering has relative to the other disciplines, if you want to call them that, is I guess the emphasis on the sort of integration of hard and soft skills and the importance of what we call enabling technologies, I guess, in the handbook. Things like teamwork, things like understanding the politics of the business, all those really important things that if you really want to solve problems, you need to be aware of and trying to manage and handle very well. And I'm sure there are people in the other areas that are also talking about that, but I think that's one of the things that we really try and emphasize in statistical engineering.
Thank you. Allison, I saw your hand up.
Really quickly, I appreciate your perspectives. And on Stefan's point to the handbook, I think the enabling technologies are, there's a lot of enabling technologies that I think I mentioned earlier that I think are really important to complex problem solving that maybe are missing from the thought that has really moved the discipline of data science forward, and I think really would also move the discipline of statistical engineering. And hopefully we'll be able to find maybe a new way to market this. So I just want to underscore that.
Great. Jeroen?
Yeah, I want to add one more term to the confusion, and that's the word analytics translator. Don't know if you've heard the term before, but in the corporate world, it's quite popular now. It's championed by McKinsey, analytics translator. What I mean by that, they say we have the data analysts, the people who develop the techniques, the guys who can do the Python coding, but there's also exactly the aspect that Stefan points out. There's the enabling skills, skills like recognizing business issue and translating them to analytic questions, and the role of a project manager, getting things done in an organization. And that is exactly the role that McKinsey has coined the term analytics translator for. And they typically describe them as being the business professionals who are not so much the technical experts, but who are the bridge between business domains and the analytics teams.
Thanks. Diego, go ahead.
Yeah, this is a wonderful point, John. This is exactly how we market the Master in Business Analytics in Geneva, using this analytics translator idea. Or also there's another word which is called purple people. I think this is by Davenport and others. It's really like these bridge keepers between both worlds. One hand, the nerds, which have the operational tools, the machine learning nerds, the statistical nerds. On the other hand, like the organizations, and there's this missing gap. And I think this is they create this bi-directional communication channel between both worlds, and this is how it could be marketed. And this is this is how I succeed to market the mindset.
Great. Yeah, I guess I'm going to use moderator's prerogative again. Two things occurred to me. One, if we look at all these terms, if we could quantify them and do a principal components analysis, there'd be a lot of zero eigenvalues. That is, if we have 10 terms, there aren't 10 unique things here that we're doing. And I guess as somebody who views himself as a scientist at times, one of the key aspects of science is precision in definitions. So you cannot say, well, I'm going to come up with a new meaning for the word acceleration or force or mass. I mean, part of science is having rigorously defined terms. So I do think it's important, whatever buzzword people come up with, that it actually describes what they're doing. And computer science is a classic one that Michael mentioned, that it's really more like computer engineering. And in fact, there's an old saying, anything that has the word science in its name is not a science, like management science, for example. Anyway, we're going to move on. And what we're going to talk about now is the future. We've talked about the past. We're going to now talk about the future. So I'm going to ask Stefan to start answering this question first. Where do you feel statistical engineering will be 20 years from now, and what will be required to get us there?
All right, thanks, Roger. So when I first read this question, I was pretty nervous, honestly. Made me think of, the previous mid-century baseball player Yogi Berra's comment about it's tough to make predictions, especially about the future. And also thinking about some epic failures in terms of prediction, like, this Titanic, oh, that could never sink. Or, Thomas Watson of IBM saying, well, I think there's a world market for about 5 computers. And so I was quite nervous about trying to make any predictions. So maybe I sort of change the question around to think about maybe an ideal future instead of a predicted future. The ideal future is almost certainly not going to happen exactly the way I'm proposing, but at least some ideas about what we might hope to see. And it's an ideal future, so I can pie in the sky here. I guess one thing I would like to see in the future is we'd have lots of success stories of people using statistical engineering to solve some of the world's biggest complex problems. Let's think big. How about helping to alleviate the problems we're having with climate change or inequality in general, or food security, or conflict avoidance and resolution, and those kinds of things. Stepping back a little bit from that high-minded goals, maybe we hope to have a thriving ISEA at least. And I think if we want to get there, maybe we would really need to have some champions with some weight behind them, like some corporate champions, like remember how Jack Welch was pretty instrumental in making sure, or helping to make Six Sigma a success. That would be really great. In terms of, like, I come from the university, so if I'm thinking about universities and Six Sigma, sorry, not Six Sigma, statistical engineering, sorry. It'd be nice if we had some more programs and courses that are basically teaching statistical engineering, if not by that name. And strong journals where academics could publish, and also case studies and so on, that people could demonstrate successes and document their successes using the methodologies that we're proposing or promoting. Yeah, so that's sort of my answer. Again, it's not really a prediction, a hope.
Would others like to comment? Christine.
So I will agree with Stefan that the question was very ambitious, connecting it to what Allison said of we're going to be on a 5-year cycle of things changing dramatically. You know, we're pushing out 4 cycles here of what's going to happen in the future. So I did sort of a best case scenario and a worst case scenario, where the worst case scenario is statisticians have really vanished in terms of relevance, and the best case scenario matches with a lot of things that Stefan had talked about. But maybe I'll tackle 2 ideas that I have about how we sort of get to the best case scenario. And so the first one is that I feel sort of ISEA as an organization right now is some people with good experience. We've learned sort of through the school of hard knocks of how to be successful at this notion of statistical engineering. But we're like people standing on the side of a pool, and we're saying, yeah, here's the mechanics of swimming, and we're doing it all standing in sort of the air. And I think at some point we need to jump into the water with our students or the people that we're hoping to accelerate their learning, and just get in there and sort of give some practical hands-on to help them sort of get on this path. And I see this as a major goal for ISEA, is we can all get there if we fumble around and sort of learn things slowly and through experience. But boy, wouldn't it be great if we could build an accelerator to get people up to speed faster, so that when at the point where they're hired, they actually have a lot of this. And so I think you know, various programs are really working on that. But I think as an organization, we need to embrace more the doing and less the talking about doing. Allison wants to comment on that. I have one other thing, but I'll stop and defer to Allison for a bit.
I'll give it back to you, Christine, but I want to second that. So we've tried for 2 years to hire someone to come in and do experiential projects with our students, and that involves getting the projects, you know, helping to do a preliminary scope and then working the students through it. Currently, we haven't been able to hire anyone to do that, even though we're paying a ton of money. And so I'm doing it.
It's available if there's a ton of money.
Because well, it's not that much, but I think for, you know, for the expectation, it's a good salary. But then so I'm doing it, right? And I'm actually going on sabbatical next year, and I just got off the phone before we started this call with my department chair, who can't find anybody on our faculty to fill behind me in teaching that course. I mentioned it was a 9-hour sequence, right? So this is a real challenge, and the biggest challenge that we face is getting the projects from the companies and getting the data and getting the non-disclosure signed so that we can actually have something that's worth working on for the students. So that would be a huge opportunity to bring industry together with academia in these various programs, and a huge member benefit would be for us to be able to have these relationships with industry to provide these opportunities, because we have to do this in our university or our students are not ready to hit the ground running. And in the data fields that they hire into, they're often hiring into organizations where they're the expert and they're 23 years old with little experience. And that's the reality of the data economy and how rapidly it's changed. Their boss may have no idea what they're doing. Best case scenario, they're going into a well-formed data science organization within a company. So, and now back to you, Christine.
Oh, and so thanks. The second idea is really sort of how statisticians get in our own way. So I think as a group, I would characterize statisticians as sort of more cautious. And so a couple of years ago, the statistical sciences group at LANL, we made a conscious decision that if we were going to compete with the data science people, we really had to be much friendlier in that first meeting, right? So I think, you know, someone comes with data, and so what we say is, oh man, I don't know, there's data quality issues, I don't know what we can do. And then you compare that to sort of a data scientist, that generic person. They say, sure, just throw some data at me, I'll do something with it. So I think our caution is both a tremendous strength, but it can also be our Achilles heel, in that we're so off-putting in that first meeting of all this caution and like, oh, all the things wrong with everything, that there's, even if we just do exploratory things in the first phase and then slowly, don't throw out the rigor for assumptions and the caution. But I think we have to get off to a better start if we're going to be embraced by the organizations, because they want us to do something. They don't want to hear about everything that they've done wrong with the data that they've invested a tremendous amount into. And so I think some of it is optics, but I do think as statisticians, we sort of shoot ourselves in the foot a lot of times with that first encounter, that why wouldn't they go to see some machine learning person who just says, send me your data and I'll do something, that's much more appealing. So I'll stop there.
Of course, they might be pretty unhappy with the result in the end when it doesn't actually give them any useful information, or so there is, I can see what you're saying, but we do have to be careful about.
I'm saying we do the same things, but the way we start the conversation has to change so that we get to be in the conversation.
Diego.
Yeah, let me just add several points. 20 years from now, starting with where we are now, and let me not speak about academia. My main activity is not in academia, it's in the professional world with companies. And currently, the failure rate of data science, AI is extremely high. So there will be soon a pain in industry because money was spent for solutions to train people, to create capabilities, in technology, in hardware, whatever. So they need to solve this issue. This is reality in a lot of businesses. So if I look now in 20 years, they will notice they have to change the way they did their things so far. So they have to look for something new at some point. And I argue that those companies who take this seriously, they will be think like a statistical engineer in 20 years, but maybe they didn't know that this is statistical engineering, what they did, but they have to do this in order to make it also to create the needed business value. And with this in mind, this is also a little bit, I hear a lot of things, discussion about academia. I fully agree on all the points which was mentioned, but I think maybe it's also the role that we as ISEA or a statistical engineering community, we go outside academia, we go into the business and say, hey guys, here we are. Just imagine if you would be on a Harvard Business Review or MIT Sloan Management cover page, statistical engineering is the future. Then we have the sales pitch. And I think this is maybe something we should concentrate. And if we succeed in this over the next 20 years, I think that all who take this data-driven problem solving and data-informed decision-making, they do it in a statistical engineering mindset without knowing that it's statistical engineering. And this is like a mission we have to go forward, outside academia, outside statistics, community, really go in the other communities.
Mm-hmm.
So it's a call for action, if you will.
Yeah. Okay, we're going to move on to our last question. After that, we will open up the floor for comments and questions from the audience. So the last question, what are the implications of failure? That is, what is the downside if statistical engineering fades away as opposed to continuing to evolve into a formal discipline? And for that question, I'm going to turn to Dick DeVoe as the first responder.
Well, thanks, Roger. And again, thanks for putting this together. And I love this question because I'm going to start with saying I don't think it'll be a disaster at all. I think it will fail, and I look forward to that because I want it to be integrated. And we've talked a little bit about terminology, and statistical engineering I think is not going to work. I remember it's about 2005, a magazine called me up and desperately wanted to know the difference between analytics, predictive analytics, business analytics, some other kinds of analytics, and I said I have no idea. They're all the same to me. That reminds me of I think, Roger, you might have been there. It was a Gordon conference where Jerry Friedman and I were on a panel. And at the end, somebody said, could you please explain the difference between data mining at the time and statistics? And Jerry said, you want to hear the long answer or the short answer? And they said the short. And he said, none. And we moved on. St. Joe's College had a program in decision sciences that was failing. There were like about 3 majors, and they were really worried about their future. So they changed the name of it to business analytics. They changed none of the courses, none of the faculty, and they had 300 students the next year. So, you know, marketing isn't a joke. And I think trying to battle these other groups and names is a losing cause. We gave up trying to battle data science at the ASA a while ago. We realized that's not happening. Look, the ACM is huge compared to us. Even the AMS, the math organization, is huge compared to us. We are the small fries. So if we take our little jousting implement and point it at those windmills, we're going down. So I think we have to figure out how to take all these wonderful things that you've all talked about and play nice and somehow figure that's the only way we're going to integrate. You've all said this, but I just want to point out some things that we've done and what we can bring to the table. We talked about these enabling tools. This is something that we do, and Michael's talked about this. You know, as computer scientists and statisticians look at the same problems from different sides of things. There was a course that back in the day, 10 years ago, we called it data mining. Now we call it statistical learning. But I was teaching a course, and my colleague, Andrea Daniluk, who ironically wrote the same kinds of guidelines for undergraduate data science programs for the ACM. So we're both at Williams, and I wrote mine that got endorsed by the ASA. She wrote hers that got endorsed by the ACM. We both taught a course called data mining. And one student, Nick Arnosti, wanted to take both of them. And the registrar balked. He said, you can't take the same course with the same name. And we convinced the registrar that it was probably okay. And at the end of the semester, I said, Nick, how much overlap was there? He said, none. He said, you said the same words sometimes, but there was no overlap. We look at different problems. What do we bring again? You know, I've been at conferences where I asked a question of the computer scientists group in industry was showing this huge workflow of what they do with data and how they bring it in and they manage it and they process it and they put it through these algorithms and they output it. And I said, where do you get the data from? And they said, oh, that's not our problem. You know, so that's a different mindset. I mean, that's a valuable thing that they do, but we bring those things we talked about, ethical concerns and data provenance and enabling tools and figuring it all. I call it common sense, but we can't really market that as the owners of that. So I think we just have to stay involved. The ASA, do you know, speaking of engineering, ABET, is that a term that's familiar to most of you? Do you know that they are writing guidelines for data science programs around the country right now? And they started this process about a year with no statisticians involved. And the ASA decided that was not a good thing. And we ponied up some money to have a membership in it. And now we are full voting members of this organization. So, you know, we were talking about caution. I know Christine said we get cautious. Well, we sent me and Kathy Ensor and Rebecca Nugent to be in these groups. And none of us are that shy about saying our opinions about things. So they heard us and they had not heard our issues, all the things I mentioned before. None of that was in their curriculum. It was all Andrea's courses for data science from computer science perspective. So I just think, you know, I think this group needs to just keep going as a group to keep talking, but I don't think we need to become a discipline by itself. I think we need to get involved and make sure that we keep being heard. I'm going to end there.
Okay, thank you. Others?
Can I ask if they listened to you at ABET? They heard you, but did they do anything about it?
They did. They changed it. They changed the guideline. No, we're having an impact. It now has maybe not as much as we want. I think maybe people like Joe Biden know what I'm talking about, but you know, not as much as we wanted, but we had definitely, it's changed. Yeah, so thank you for asking.
Michael, go ahead.
Yeah, no, I just want to amplify what Dick has said. So there is now a new journal between IMS and ACM on data science. And that was a bit of a fight I had a little involvement there really for more the IMS side to make sure that IMS was respected, and it has been. And so, you know, I think that data science, for better or for worse, will probably survive. I think that there's now enough users of it. It really came from industry mostly, but, you know, but it has really been picked up. And I think the best action item here for this group is actually to own that, you know, to try to own that and say part of data science is not just the computer science of building the pipeline or whatever, it's also the, you know, the inference issues, but it's also the design issues. And I think that word in building issues, but there's a statistical perspective on design that we bring. And if I think you would kind of own that and highlight in the connection to analytics and to business schools, that's kind of a unique voice that you would have there, and just kind of own that. And I would deprecate this statistical engineering. I do think it's a provocative thing, and it is a conversation starter, but it ends the conversation, sadly, very quickly thereafter. And whereas data science is not ending, and the problem is that if you abdicate and you don't say, yeah, we own it, then it is getting picked up. It has been by computer scientists. They're just larger and more connected. They are also fighting the AI buzzword too. But I think eventually AI will kind of be owned by the classical AI people who want to do, they have a certain class of applications in mind. They're not trying to own the data analysis for, you know, everything else. And so there is this term to be kind of grabbed by people, which is data science. And so I loved what Dick just said, that, you know, angle in and be very present in those conversations. But as Christine was saying, when you're in those conversations, don't present yourself as the pessimistic, you know, nothing's going to work statistician. Say, no, I'm the builder type statistician. You haven't seen people like me before, but I exist. And sometimes I'm in business schools, sometimes I'm in other disciplines, but I exist and I want to contribute here and I want to make data science. So one thing to do is maybe contact let's see, I guess it's John Lafferty is one of the people who's an editor of the IMS ACM Journal of Data Science. He's a little more of a theoretical machine learning stat person. He's kind of a bridge, but he's not I wouldn't call him an engineering mindset. But he needs to kind of maybe be, maybe one of you would volunteer to say, hey, do you have our perspective in there? One of the editors should be a person like me. And just, yeah, continue to kind of don't let opportunities like that pass by. And don't let data science be owned by those computer scientists, and don't let it be deprecated as kind of the term given to the boring parts or you know, whatever. You know, so.
Okay, moderator's prerogative again. I guess thinking about what Michael and Dick just said, I've been kind of frustrated my entire career as a statistician in this way. I read, you know, Box and Tukey and all these people when I got my PhD in the 80s. And then when I interacted with the statistical community, and I don't want to pick on ASA, we'll say the statistical community, in the 80s and 90s, nobody wanted to talk about solving real problems. They wanted to talk about math. And Box said it before I even thought of it. He said, why do we want to be second-rate mathematicians when we can be first-rate scientists? He didn't say engineer, but he said scientist, which really resonated with me. And I kind of felt like I spent most of my career banging my head against a wall, trying to convince people that he was right. We didn't have to be mathematicians. We could be good scientists. And then more recently, I feel the statistics community has kind of waken up to that and realized, you know what, we don't have to be mathematicians. Now we're going to be computer scientists. And it seems like the emphasis within the statistical community is on computation and coding. And, you know, coding's great, computation's great. The problem is there's already this discipline called computer science. And that's their discipline, and that's what they're best at. So I know Michael's got a joint appointment in both camps, but for those of us that don't, that are statisticians, I'm never going to be a better computer scientist than a computer scientist. And so while on the one hand, it would be great if we could take these ideas that we're talking about that I think we all agree on and integrate them in with the statistics community, I personally don't sense a lot of receptivity. That's my own personal opinion. Allison.
I'm going to give you maybe a slightly different viewpoint. I've had my PhD for more than 20 years, and I chose to go into a business school because prior to getting my PhD, I was in a consulting role, and I went back to get my degree. And my goal in going back was to get 3 letters after my name so I could charge more. That was kind of my mindset at the time. I never ended up back in industry or in consulting. I ended up in academia. But I've never been a part of a program or a university, and I've been at multiple universities in statistics programs, but always in the business school. I've never seen one that didn't focus to some degree on problem solving, and that includes my current university, both in the statistics department and in the business school, and we, you know, we collaborate quite well. I'm definitely in the more applied side, but I think that there are many programs out there that are focusing on problem solving. In my PhD comps, we had a case study as part of our comps. We had all the theoretical stuff, plus we had to solve a case study. And so I think it's there. I just think there are a number of theoretical programs, but I don't want to overemphasize the fact that students are being taught to solve problems, and that's going out into industry, and all of the students that we place out there have at least some degree of that. Now, whether they use good practice or it's consistent with ISEA's vision of that practice, I can't answer that.
Okay. Diego, and then we're going to open it up to questions from the floor. Go ahead, Diego.
Yeah, and maybe just share another viewpoint going in line with what Michael said. It's about leadership on the term, and I can share your experience from Switzerland. So we have consulting since 2016, the Swiss government on data science. So basically the Federal Statistical Office. And we, for the time being, basically they set up a data science competence center. We defined at the government level the ownership of data science, of statistics they already have, because it's the Federal Statistical Office, like the US Census Bureau. You have several of those. In Switzerland, we only have one. There's a data science competence center. We're currently doing a data science strategy for the complete government in Switzerland. And now, why I'm telling you this, ownership of this thing is the Federal Statistical Office, has ownership of data science. This means we were able to define data science for the Swiss government. And we define data science, as you know, Roger, as data-driven problem solving to solve complex unstructured data-rich problems. So this is redefined on a governmental level for the Swiss Confederation. And this is due to leadership by official statistics community, which have like the leadership already in what's called statistics for public good. And we go now forward to make this data science for public good, and including, if necessary, needed AI technologies. So this is just to make this point. This has to do with leadership, and it has to be led, and maybe also by community who already have shown trustworthy statistical production, like official statistics, which should take more leadership on this, because they have the trustworthiness of the public, so they have the trust label. So this is a little bit more difficult if you come from academia. But if you go outside in a governmental setting, I know with you it's a little bit more difficult, but at least in Switzerland, this is how it's working wonderfully now. And really can start, if you want brainwashing, we can create curriculum, we can connect with universities, with our ETH, to really make this happen a reality. So there are plenty of things I can share you afterwards.
Okay. So we are going to move on to open Q&A. So if you want to put a comment in the chat box, we did have a couple come up previously. I think they're more comments than questions, but I will read them if anybody wants to comment. The first one, I'm at a Polytechnic University, so I think statistical engineering would actually sound more appealing to our students than data science, but our administration wanted something called data science and AI, so that's what we call it. The second, regarding tool-centric versus problem-centric, a value that statisticians bring to problem solving is the ability to frame seemingly unique problems as problems that we've seen and solved before using particular tools. Any comments on those? Michael.
Yeah, I disagree about statistical engineering as something that students will gravitate towards. Yeah, and again, we've done a data science program at Berkeley, and we have 3,000 undergraduates, freshmen taking it every year. 3,000, and it was not a required course. It's because they perceive that that's the future.
Now
that
you're
terminology.
talking about a degree program, or you're talking about the one course, the intro course?
No, that's the intro course, but a lot of them we had, like, I think we're up to 800 in the major. There's a data science major now, and again, just in a couple of years, it's up to 800. And this is Berkeley, but still, no, this is the mindset. A lot of young people, for whatever reason, feel, oh, I see data science, that empowers me. That's the future. You know, computer science is a little deprecated, even kind of relative to that. Whereas data science really wins out. But we have a lot of people in the stat, so the stat major has grown too. The econ major have grown, but data science has grown much, much faster than any of the above. But I cannot imagine, I do not believe that if we had a data science, or sorry, a statistical engineering class, it would be 3,000 people. It's inconceivable to me. So own this, really, yeah, this data science thing is something that should be not left to the computer scientists. And I'm encouraged by some of the comments here. You know, own several chunks of it and be omnipresent in the conversation. And it's not an asymptotics conversation. It's not just a tools conversation. It's got real use cases, and keep owning this. And when you talk to the campus, say, oh, do you want data science? Yeah, we provide that. We do that. And maybe you'll partner with a computer science colleague to help do it. But absolutely, that.
Great, thank you. Others? Go ahead, Christine.
Just latching on to the second part of the comment. Can you read that again, Roger?
I can. Regarding tool-centric versus problem-centric, a value that statisticians bring to problem solving is the ability to frame seemingly unique problems as problems that we've seen and solved before using particular tools.
So I think that connects to something that Stefan said early on, is that we cover this very wide array of problems. And I do think that, you know, us focusing on sort of commonalities and sort of classes of problems, that feels like it would be a useful endeavor to be able to sort of highlight some categories of problems and sort of starting points for them. That feels like something that would be really value added, because I think there's a lot of, you know, rediscovering the wheel in different scenarios. And so some of the packaging of categories of problems feels like an opportunity, and, you know, could be an accelerant again for people to just launch into a variety of problems more efficiently and to be following some best practices.
Thank you. Another question came through. Is there such a thing as a statistical engineer? Like a data scientist, this seems like a unicorn. And I'm assuming the person means someone who has all the requisite skills. Now, interestingly, again, I'm going to take moderator's prerogative. Interestingly, we're several hours in to this summit on statistical engineering, and it's never been defined. So according to the handbook that Lynn mentioned, the definition is the study of the systematic integration of statistical concepts, methods, and tools, often with other relevant disciplines, to solve important problems sustainably. So my answer would be, because we're talking about integration, and I loved Michael's little triangle with the economics, computer science, and statistics. No, there is no such thing. It is a unicorn. It's almost always done by teams that are going to require multiple skill sets. There is no one individual that has everything that's going to be needed. That would be my 2 cents worth, but I'll open it to the panel as well. Christine.
So mine's a little bit tongue-in-cheek, but I do think that the labels that are most successful are the ones that are poorly defined. And so I think our precision in defining things sometimes is a liability. That, you know, I think there's, if you look in industry, I bet there's a lot of people who have a label of statistical engineer. And so us, you know, it doesn't seem to me like a precise definition is always beneficial. I think for me it's comforting, but I think loosely defined actually captures a lot more interest And that's been demonstrated with a lot of these terms that are used very sloppily, but they gain advantage from it.
Diego.
Yeah, I think, as you may know, I call myself a statistical engineer, and this is my best job description. And I extend a little bit the definition of statistical engineering, including any tool which makes sense, including machine learning, big data analytics, whatever you want. And I really focus a little bit on this, what was mentioned by Sharon, this translator role. So this is guy who knows a little bit of everything, and the problem comes and helps to assemble the different pieces, to engineer basically, to help to define the problem. It's clear for doing it, you need a team. But I think it's the engineer's responsibility to know from what you need what element. And as such, I see myself as a statistical engineer. And on the ISEA webpage, I had the pleasure to give the first webinar last year. It was, no, this year, this January or February, where you can also find the slides and the recording where you see a little bit this idea. This is the best job description for my person after 20 years of experience. I call myself a statistical engineer, but I extend a little bit the definition of the handbook.
Okay, we have another comment. It's not really a question, it's a comment. In every ISEA event, there is a discussion of the need to change the name and market our ideas, but we keep discussing what it is and what the process is. We should concentrate on the name and the marketing. I think that's yes. Okay, last call.
Can I
we have 4 minutes.
Yeah,
go ahead, Diego.
Marketing is also, for me, who is the audience? And I fear a little bit, I'm still young, etc. But we're focused on the wrong audience. We don't have to run after statisticians and get them involved, etc. We have to open ourselves to new audiences. We are open to hear us. So outside statistics communities, outside, really go in the business world, go in the operational world. So I think this is also a little bit, we have to extend the scope a little. This could something which could help for the market. Because if you can prove that it's working there, the others will then join us because it's working.
Jeroen.
I want to build a bit on what Diego is saying, and that is a bit more in what Peter Drucker would call the outside-in perspective. I think it's very important not to overemphasize on what we believe would be a good name or a good definition, but to follow quite closely what is happening in the world around us. And to give just one example, here in Europe, the European Union is preparing a legal framework for what they call trustworthy AI. And that is going to be a legal framework that's simply mandatory, and that is going to have a lot of impact on how you can apply algorithms and machine learning and AI. And where that opens opportunities for us is that part of this trustworthy AI framework talks about that algorithms in many cases should be explainable and interpretable. They talk about how you should demonstrate that you use the right data. They talk about how you should demonstrate that your algorithm doesn't create a bias. And I think that is the important thing that we should do, is follow that sort of development and recognize that those are questions that we are particularly well suited to offer some insights to, rather than having this inside out perspective, what we believe would be a good name.
Well, I'm going to end the session with a comment I just received from Lynn Hare. I've been unhappy with the name Lynn for 79 years, but in time I've gotten used to it. But I now understand the academic's plight in trying to sell statistical engineering to students and other faculty members. In my practice, I ignore them and I focus on teaming to solve problems. Excellent session. Thanks, Lynn. So as we close this session out, I just want to thank the panelists. I really appreciate all the ideas that we shared. I think we had a reasonable amount of disagreement, which is always good, but also some key themes that came out of it. So thanks so much to everybody, and I'm going to turn it over to Nathaniel.
Yeah, I want to echo my thanks on behalf of the audience. That was an excellent session, a lot of really interesting thoughts and perspectives.